A warm good morning to one and all. Respected delegates, eminent personalities and participants gathered here. Science is a way of life. Science is a perspective. Science is a process that takes us from confusion to understanding in a manner that's precise, predictive, and reliable. These are the words of American scientist Neil Tyson. Chemistry is all around us, from the air we breathe to the water we drink, from the food we eat to the medicines we take. It plays a crucial role in our daily lives. The chemistry department of Sacred Heart College, Thevara, was established in 1945 with an intention of providing the best education to all those who have the passion to learn chemistry. Professor K.V. Thomas Endowment Seminar is the most prestigious event organized by the Postgraduate and Research Department of Chemistry. For over 2 decades, we have proudly organized 22 national seminars, including 4 international symposiums. This is the 23rd edition of Professor K.V. Thomas Endowment Seminar. Human beings are living in an era of science and technology. Material science is a discipline that combines chemistry, physics, biology, and engineering. It is a foundation stone of modern technological societies. I take this opportunity to welcome you all wholeheartedly to the prestigious 23rd Professor K.V. Thomas Endowment National Seminar on Frontiers in Material Science, organized by the Postgraduate and Research Department of Chemistry, Sacred Heart College, Thevara. I request everyone to raise for the college anthem.
Stopping by the shimmering shows of time, musing on the timeless truth sublime. Seek aside a gleam on flaming wings. Sacred Heart, the soul enchanted sings. Blessed are we on this praising shore, blissfully gleaning pearls of pilgrims on these pastures green, seeking joy, hinterlands unseen. Sacred Heart, abode of light, shine on bright, abiding heart. Sacred Heart, shrine of light, shine your beams, make us one at heart.
I'm extremely delighted to call upon Dr. Ginu George, Head of the Department of Chemistry and General Convener of this seminar for the welcome address. Ma'am, please.
Good morning, respected dignitaries, esteemed guests, faculty members, students and delegates. On behalf of the Department of Chemistry, Sacred Heart College, I extend a warm welcome to all of you to the 23rd Professor K.V. Thomas Endowment National Seminar on Frontiers in Material Science. This seminar serves as a platform for intellectual engagement and collaboration, focusing on advancing material science with sustainability at its core. To begin with, I extend a heartfelt welcome to our chief guest, Professor C.T. Aravind Kumar, Vice Chancellor of Mahatma Gandhi University, whose exemplary leadership in academia and research sets first support and encouragement are integral to all our endeavors. Welcome, sir. I warmly welcome Dr. Pradeep Pujari, Raja Ramanna Fellow and former Director of Radiochemistry and Isotope Group, BARC, Mumbai. Sir, your distinguished contributions to the field of radiochemistry add immense value to this occasion. Welcome. Next, I extend a special welcome to our keynote speakers, and beginning with Padma Shri Professor T. Pradeep, Institute Professor, and Deepak Parikh, Chair Professor at IIT Madras. Welcome, sir. Professor Pradeep is a pioneer in nanotechnology-based solutions for affordable clean water and a recipient of numerous accolades for his path-breaking work in material science. I also welcome Professor Sebastian C. Peter, a renowned
academic and scientific institutions. Sacred Heart College, which has a long history of 80 years in imparting knowledge, is so proud to host all these wonderful scholars here, luminaries, scientists, and everybody who is a part of this event. And I once again congratulate all the participants, organizers, and the Faculty of Chemistry for this wonderful achievement. Thank you very much.
Thank you, Professor. On this auspicious occasion, it is our privilege to have Honorable Vice Chancellor of Mahatma Gandhi University, Professor C.T. Aravind Kumar, among us today. May I kindly request Professor to address the gathering and to inaugurate the 23rd Prof K.V. Thomas Endowment National Seminar. Sir, please.
എല്ലാവർക്കും നമസ്കാരം. Very good morning to all. The chair of the session, Dr. Varghese Kachapalli, esteemed Padma Shri Professor Pradeep, Dr. Jinu George, Professor Pujari, Professor Biju, Dr. Ammu Rosen, other distinguished delegates, guests, and my dear friends. It's really an honor for me to be here in the morning to inaugurate this prestigious Prof K.V. Thomas Endowment National Seminar of this college. And we proudly say chemistry is a central subject which connects all.
Highly interdisciplinary in nature. Now there is no chemist, no physicist, no electrical engineer. They are all pulled together. The material science is all encompassing. It encompasses all the discipline, and that's why it's called material sciences, even for the departments that were known as metallurgy or solid state physics or solid state chemistry, or distinct engineering branches. So they have all come together to develop the materials, and you require the expertise of all kind of expertise or disciplines to get the right material. And when you talk about material, it's everything. Is here, if you look up, down, side, the lamps, the lights, everything is material. And it is not the role of one discipline to achieve perfection. Now, when you talk about the frontiers in material science, there are few things that comes to your mind. It is huge. Actually, the bouquet is huge. The number of the subjects I use. But I would put it, I have kind of categorized them, into say energy. Just now, Professor Arvind Kumar talked about the environment, and of course he touched upon energy. I would put water and materials related to that. The first and foremost is, the materials related to batteries. That is the prime focus. Now, it is not something new that people are working on materials for batteries. People have worked materials for batteries for many, they've been working. But it is always, it's ongoing. You try to improve the properties, you try to improve the energy density, you try to improve the life of a battery, and so on and so forth. So it's a huge amount of focus on these materials. Let me tell you about the solar cells. The solar cells, people are working, and we had solar cells many years ago. But still, the focus is on solar materials like perovskites. The focus is on perovskites to again improve the energy density. That from the certain surface area, you are trying to extract the maximum energy from this. I told about the storage, energy storage, about the battery. Another thing is fuel cells, materials for fuel cells. And fuel cells is the one, which is going to give you energy from hydrogen. The hydrogen will be converted to electrical energy. And this is another focus area that we talk about. Supercapacitors. So these are the things, are still in the frontiers. Thermoelectric materials. Thermoelectric materials are materials which convert the heat energy to electrical energy. And this is also another focus area, and this huge amount of work is going on with this. Now, water. I talked about water. And there is someone here in this audience, Professor T. Pradeep, he is going to talk more about it. But materials for giving you clean water, a variety of materials, and materials related to technologies for water resource management, and so on and so forth. So that is another focus area, and we are going to hear much more from him in his lecture. The next focus area is electronics and photonics. So what are the frontier areas now people are, maximum number of people are working, or it is being talked about, are the 2D materials. Two-dimensional materials like graphene, phosphorine, and recent addition is the transition metal dichalcogenides. So these are the focus areas. Second is the topological materials. Topological materials are insulators, but they conduct electricity on the surface. Things like bismuth selenide and mercury telluride and so on and so forth. You talk about metamaterials, the artificial materials with very tailored properties. That is another focus area. Then we come to biomolecules and bio-inspired material sciences. That is tissue engineering, scaffolds, like you create artificial skin. You will be surprised that the skin, there are skin banks, and I know that there's a huge deficit of skin donation. People are not aware about skin donation. In case of accidental fire hazards, it becomes extremely difficult to source skin, and imagine if the patient is not able to or cannot provide the skin for repair of the wound or damages, then it is a huge problem. And I have been associated with, through my Rotary Club, of conducting camps for poor patients, for giving them, and I know, I am aware how much research is required, or how much requirement is there for this kind of tissue engineering related research, where you can produce artificial skin. Materials mimicking, this properties of natural materials. Like you can talk about the self-healing materials like hydrogels. You talk about nanomedicines. There are nanoparticles and nanostructured materials for targeted drug delivery and imaging as well as therapy. So these are, it's not something new, but the new paradigms or new kind of, different ways that people are looking at it and the different approach that people have taken to revisit or continue research in this and to give you the product. Next is the computational material sciences. People talk about this materials genome initiative, where you create a huge amount of database and you also develop the computational tools for discovery or predicting the properties of new materials. And in this context, the machine learning has come in a big way, is coming in a big way, or it is already there to design new materials and of course use a multi-scale modeling. It is not easy to predict the property of a material through ab initio calculations. If you want to do a theoretical calculations, the theoretical scientists or computational scientists, they will tell you that if you have 50 atoms, a molecule, or say 30 atoms or 40 atoms, how much time does it take just to optimize or get the minimum energy configuration? It consumes huge amount of computational time, or say computer time. So what are the options? Now, you must have heard about the Nobel Prize, this year's Nobel Prize, where AI-based tools, have been used, and that is David Baker who got the award, and it could predict the three-dimensional structure of protein by just giving you the sequence of the amino acids. It's a huge development, and the development which is going to revolutionize the way people do computational material science. And you will be surprised to know that this tool AlphaFold is now in the open domain. One can use it for non-business purposes. It is one can take AlphaFold and work with it. It has made a huge difference, and the impact is going to be huge in biology and medical sciences, and so on and so forth. As a man from the Department of Atomic Energy, I would like to tell you a few things that we are currently, engaged in. The Department of Energy, Atomic Energy, has developed the technologies, and it's not today, it's almost 70 years that we are existing here, that we have developed technologies in-house for, what you call the ore to core, that all the nuclear materials or the materials that relates to nuclear reactors, the technologies and the processes have been developed. And today you have all the nuclear reactors that we have in India, the entire, like your pressure tubes, your fuel cladding materials, everything that you see, the alloys have been developed. And it has not come easily. You cannot just take a material or roll or make a cladding material. The deep study you have to do, you have to have a proper understanding of the microstructure and its property correlation. This is very essential, and that has been mastered. And it's a fundamental sciences that has helped build materials for nuclear reactors, which can withstand high temperature, high radiation field, and give the optimum properties that is desired. So what is the new paradigm or new thinking on material science in Department of Atomic Energy? Of course, we are engaged in the fundamental research in all the areas that I talked about, with the topological material, or the phosphorines, or the graphene related, or magnetic materials, or bio-mimicking materials. These are all, in fundamental research level. But what we need immediately, and what we wish to implement the technology, as soon as possible, are accident-tolerant materials. This has become very, very essential post-Fukushima. People talk about, nuclear accident in Fukushima. It's not a nuclear accident. Let me tell you, of course, it is accident in a nuclear facility, but what happened was you had a power failure. The DG sets were also, the secondary backup power failure was also because of flooding that didn't work. So we have something called a loss of coolant accident, LOCA. That the fuel, even if you shut down the reactor, you have to have continuous, you have a continuous flow of water to cool the core. Otherwise, the core will melt. So that is where we are talking about now accident tolerant materials. That is, the fuel pellets will be coated with, and if you have a hot metal and you have water, there will be hydrogen formation, production, and that was the main reason of the problem in Fukushima. So with this, I wish the conference or this seminar all the success. And once again, thank the organizers for inviting me here and giving me the opportunity to interact with you people, the students, and of course visit this esteemed institutions. Thank you so much.
Thank you, sir, for your enlightening words. Now, we are heading for the release of our proceedings. May I kindly invite Professor P.K. Pujari to release the proceedings and Professor Biju C.S., Principal, Sacred Heart College, Thevara, to receive the same. I would also like to invite Dr. Ramakrishnan S. and Dr. Thomas Koti Jose, editors in charge and faculties in the Department of Chemistry, to join on the stage. Thank you all. All delegates can scan the QR code behind the tag for receiving the soft copy of the proceedings.
Ladies and gentlemen, it is now time to felicitate and honor the distinguished guests who have graced this occasion with their presence and contribution. To begin, it is my honor to invite Padma Shri Professor T. Pradeep, Indian Institute of Technology, Madras, to felicitate the occasion.
Good morning. In 3 minutes, what can I tell you? Frontiers of material science was a vision. Well, 23 years ago, Professor K.V. Thomas thought about that. The frontiers of material science is shifting. 25 years ago, well, about 35 years ago, I did my PhD. So during those days, material science was considered as a sort of a dirty subject. Materials chemistry was, well, somewhat like a lesser discipline than organic chemistry. But today, material science is at the frontier, and we are all using a mobile phone, keeping energy in the pocket because of material science. But what is material science of today? Friends of mine take carbon dioxide from the air and think about making food in the lab. I mean it, making food in the lab because of material science. Friends of mine think about material science of today? Concrete. Friends of mine 8% of the global CO2 carbon dioxide is due from the air concrete. and think about
Can we
making
make
food in
new
the lab.
concrete of the Roman era? I mean,
Without
CO2,
making food in the lab.
well, we
because of
rediscover
Friends
materials
of mine,
different
what
kinds.
is material science of today?
Professor
Concrete.
Thomas would know
Friends
that
of mine,
90% of the global
coastline,
CO2
carbon dioxide
is due
from
to
the
our
air.
coastline is increasingly threatened because of climate change. How do you protect the coastline? Well, you bring in rocks. But we don't have rocks now. We have to get rocks from Rajasthan. But that is carbon dioxide. Can we make new rocks? Well, rocks by taking sand from the seashore and convert that to rocks in a sustainable fashion, put them on the seashore, and eventually they become sand again. Can we think of new materials? I told you this much to tell you that just go outside and you will see frontiers of materials. Just that you have to think about them. Chemistry today enables you to think about new frontiers. In 1972, we started the first master's program in materials in the country. Material Science MTech. By 1989, we started the journal Chemistry of Materials. And these subjects, of course, I can go on to tell you so many exciting things that have happened. But today, around you, new materials are born. There are friends of mine who make this sheet of paper using calcium carbonate, seashells. This is fixing carbon dioxide. This is industry for Kerala. So likewise, the 100 things that are changing the world. Yesterday, I was sitting in a seminar hall of my students in an innovation and entrepreneurship course. Students talked about making cotton from carbon dioxide in a flask and a reaction vessel. Fascinating frontiers are there awaiting you to explore. All the very best to you. Thank you very much.
Thank you, sir. Moving forward, we have the privilege of inviting Professor K.V. Thomas, former Central and State Minister, Special Representative of Kerala Government, and former Head of Department of Chemistry, Sacred Heart College, Thevara, to come forward for the felicitation.
Respected guests who have come to this national seminar on frontiers of material science. At the beginning, I would like to apologize for coming a little late. I was trapped in a traffic jam, just walking distance from here. These are some of the problems developing cities like Cochin is facing. Now I am coming from Delhi, and I have been in Delhi for the last 40 years. Today, when I look at Delhi, one of the serious problems is the smoke and fog. In 1970, when I reached Delhi for the first time, I was happy and proud of our capital city. It is as good or better than many of the capital cities of Europe. But today, I want to run out of Delhi because it is smoke and fog. In 1980, when I went to Delhi as a member of parliament with my family, in the month of December, January, we used to rush out of our flat to catch the ice pieces coming from the heaven, or from the sky. Now there is no ice pieces, it is only smoke and the water spray given by the Delhi municipality. So this is an area where we have to seriously think about it. I am just making an example of the problems we are facing. Now even there is a thinking that the capital should be moved out of Delhi. The parliament is there, the Rashtrapati Bhavan is there, or secretariat is there, but government is giving holidays to the students and to the employees to sit at home and work. And you know, these are some of the issues which the country faces. Another area where I have happened to work with Professor M.S. Swaminathan, who is the father of the Green Revolution in India. I know him from his younger days. He was born and brought up in Alleppey, then went to Chennai. Later he was a man who worked with Pandit Jawaharlal Nehru when we decided that India should have a agricultural policy where we have to stand on our leg. When we had the independence, about 75 years back, it was from ship to mouth. From that stage, India has developed. We are one of the largest food grains exporting countries in the world. The contribution goes to the farmers as well as to scientists like M.S. Swaminathan. Now, when I was a student here in Sacred Heart College, we were under the Madras University. And later we were under the Kerala University. So many ministerial work, either we have to go by train to Chennai or to Trivandrum. Those days, it was the coal trains, coal engines that were used. From that coal engines, we went to the diesel engines, to the electric engines. And day before, I had the opportunity to participate in a science seminar in Delhi that we are going to use hydrogen. So hydrogen engines are coming. So these are the fast developments taking throughout the world, in India also. So this particular seminar today, conducted by my colleagues, I congratulate them. This is the fourth generation. When I came here in 1962 as a student, Professor M.B. Varghese was the head of the department. At the time it was under the Madras University. The fourth generation leaders have taken the steering of this department, famous department, and I congratulate all of them so that they continued this endowment seminar for the 23rd year. My best wishes. Thank you very much.
Thank you, sir. Now, to commemorate this memorable occasion and as a token of our appreciation, we would like to present a memento to our esteemed guest. This memento symbolizes our deep respect and gratitude for their valuable contribution to our seminar. I invite our beloved principal, Professor Biju C.S., to hand over the memento to Professor C.T. Aravind Kumar as a token of love. I invite Professor C.T. Aravind Kumar to kindly receive the same. I request the principal to present the memento to Professor P.K. Pujari as a token of love. I cordially invite Professor P.K. Pujari to receive the same. request the principal to present the memento to Padma Shri Professor T. Pradeep as a token of love. I cordially invite Professor T. Pradeep to receive the same. Thank you, professors. Now, let me call upon Dr. Ammu Rosenjos, Assistant Professor of Department of Chemistry, Sacred Heart College, Thevara, and the Organizing Secretary of the seminar to propose the vote of thanks.
Thank you. Respected dignitaries on the dais, dear professors, my colleagues, dear students and the participants, good morning to all. On behalf of the Department of Chemistry at Sacred Heart College, Thevara, it's my privilege as the Organizing Secretary of 23rd Prof K.V. Thomas Endowment National Seminar on Frontiers in Material Science to deliver the vote of thanks for this inaugural session. First and foremost, I express my heartfelt gratitude to our esteemed manager, Reverend Father Verghese Kachapalli, for his unwavering support and guidance that have been instrumental in organizing this event. Our sincere thanks to our principal, Professor Biju C.S., whose encouragement and leadership have provided us with the confidence to host such a prestigious event. Thank you, sir. We are deeply honored to have Professor C.T. Aravinda Kumar, Vice Chancellor of Mahatma Gandhi University, Kottayam, as our chief guest for the inaugural session. Sir, your inspiring address has set the perfect tone for the seminar, and we are truly grateful for your presence. Thank you, sir. We are equally thankful to our special guest, Dr. P.K. Pujari, former Director of the Radiology and Isotope Group at BARC and Raja Ramanna Fellow, for gracing the occasion and for your valuable contributions to the field of material science. Thank you, sir. Our heartfelt thanks to all the distinguished speakers, including Padma Shri Professor T. Pradeep, Professor Sebastian C. Peter, Professor Chalamala Reddy, and Professor Kana Sureshan, as well as the session chairs for the invaluable contributions to this seminar. Your expertise and insights will undoubtedly enrich this event and inspire all of us. I would like to convey my special thanks to Professor T. Pradeep for his truly insightful and inspiring words. Thank you, sir. I would like to express my sincere thanks to Professor K.V. Thomas for all the support and guidance he has provided throughout the seminar organization. My thanks to the exhibitors and all the sponsors. They include SERB, BRNS, Cochin Shipyard, BPCL, Interfield, MPDA, Coconut Development Board, Nairo Research, Sinsil, Calgun, NICE and Spectrochem Limited, whose generous support has been vital for the success of the seminar. I extend my special thanks to our head of the department, Dr. Jinu George, and all the other faculty members for the tireless efforts in planning and organizing this event. I also remember with gratitude our former teachers, whose legacy inspires us to strive for excellence, and extend our thanks to the teaching and non-teaching staff and all the volunteers for the invaluable assistance. We are proud to have over 100 presentations in both oral and poster sections. I extend my sincere gratitude to all the judges for the time, expertise and commitment in evaluating these presentations. And I express my gratitude. I would like to convey my special thanks to Professor is what makes the seminar vibrant and meaningful. Finally, I wish everyone a wonderful and intellectually stimulating experience. I would like to convey my special thanks to...
Thank you, ma'am. With this, we have come to an end of the inaugural ceremony. Now, there is a group photo session here, and I request all the delegates to stay back for the same. After that, there will be a short tea break, and it is arranged in the Marian Hall. Volunteers will lead you to the venue. I request you all to gather back at sharp 11 a.m. in the Malicious Hall for the Plenary Lecture 1 by Padma Shri Professor T. Pradeep. Few more announcements. Participants of the oral presentation competition on the topics Organic Chemistry, Chemical Biology and Applied Materials and Interfaces can hand over their presentations in pen drive to Dr. Ramakrishnan S. and Dr. Thomas Kuti Jose. The competition will commence at sharp 1:30 p.m. in Physics Seminar Hall in the first floor. Volunteers will be happy in guiding you to the venue. The oral presentation competition on the topic Applied Nanomaterials will be held in the Malicious Hall at sharp 3:15 p.m. Participants can hand over their presentations in pen drive to the technical team sitting in the left side of the hall near the podium to Dr. ABTG and Dr. Jason MJ. Those who are participating in the poster presentation competition can hang their posters at Avogadro Alley in the premises of the Department of Chemistry in the first floor during lunch break before 3 p.m. Evaluators will be there at 3 o'clock. For any queries, kindly approach the volunteers. Please be diligent about attending all sessions. Thank you. I request all the delegates on the dais to take their seats in the front row and all participants to come forward for the group photo.
We are moving on to the first plenary lecture by Padma Shri Professor T. Pradeep on the topic, Can Water Microdroplets Make Soil? A Path to Sustainable Nanotechnology. The session will be chaired by Professor C.T. Aravind Kumar, Vice Chancellor of Mahatma Gandhi University. It's my honor to introduce him to the gathering. Professor C.T. Aravind Kumar is the Honorable Vice Chancellor of Mahatma Gandhi University and holds honorary positions as the Director of the Inter-University Instrumentation Center, Coordinator of the National Center, SAIF DST, and the Director of the International Center for Polar Studies. He has completed 20 national and international major research projects, including the prestigious Obama Singh 21st Century Knowledge Initiative with Duke University, USA. I cordially welcome you, sir, to chair the session. Sir, please.
Yeah, thank you very much. So again, it is an honor for me to introduce Professor Pradeep. In fact, to chemistry audience, I don't think Professor Pradeep need an introduction, but still, since the situation demand, I have to introduce him. He is one of the most prominent researchers of India in chemistry and materials. He is a fellow of all the 4 science and engineering academies of India and 6 academies in the world. He is an institute professor at the Indian Institute of Technology, Madras. He is a Deepak Parekh Institute Chair Professor and is also a Professor of Chemistry. He studied at the University of Calicut, so he is the son of the soil. Then Indian Institute of Science, Bangalore, UC Berkeley and Purdue. His research interests are in the molecular and nanoscience materials. He is an author of over 570 scientific papers in journals and is an inventor of over 100 issued patents. He is involved in the development of affordable technologies for drinking water purification, and some of them have been already commercialized. His pesticide removal technology has reached about 10 million people. His arsenic removal technology, approved for national implementation, is now delivering arsenic-free water to about 1.3 million people every day. Along with his associate, he has incubated 7 companies and 3 of them have production units. He is the recipient of several awards, including the Shanti Swarup Bhatnagar Prize, B.M. Birla Science Prize, National Award for Nanoscience and Nanotechnology, India Nanotech Innovation Award, J.C. Bose National Fellowship, and National Water Award. He has won the World Academy of Science TWAS Prize in Chemistry for the year 2018. Then the nation conferred the most prestigious civilian award, Padma Shri, on him in 2020. Well, I can go on reading, several of his awards for another maybe about 30 minutes, but I'm not going to do it. So I'm really cutting down. I'm sorry to the organizers. Then he is the author of the introductory textbook, Nano, the Essential, and he is the author of the monograph Nanofluid, and an advancement textbook, a textbook of nanoscience and nanotechnology and so on. He is on the editorial board of a series of most prestigious journals across the globe. And interestingly, he has authored popular science books in English and Malayalam, and is a recipient of, this very important recipient of Kerala Sahitya Academy Award for Knowledge Literature. He has received the Lifetime Achievement Research Award of IIT Madras and Distinguished Illuminous Award of Indian Institute of Science, Bangalore. As part of the philanthropy, he supports a school in his village where over 500 students are on roll. So this is a very brief introduction about Professor Pradeep. With this introduction, I call upon Professor Pradeep to deliver his lecture. Thank you.
Slide is working. Maybe you could come to the front in case the screen is not visible, because lettering can be small. Okay. We're set? Okay. A very good morning to all of you, and let me first of all thank Professor Aravind Kumar. Well, first of all, let me greet him as Vice Chancellor of Mahatma Gandhi University. We have worked together on many occasions. Most recently, the Higher Education Reforms Commission of the Government of Kerala. Well, I chose to talk about a topic like this because the title given to me was The Frontiers of Material Science. So I chose to talk about one paper which came out this year. Then I saw that my lecture time is a little longer than what is normally given to these kinds of lectures. So typically it is 40 minutes, so it is 1.5 hours. So I added a few other things that they are also this year's work. So Frontiers of Material Science. Today I was supposed to be at the Royal Society in London for an India-UK meeting. But because this college had invited me several months in advance and had promised to be here, I canceled that. So glad to see you all here on this occasion. The subject that I chose to talk about, can you come to the front, please? I asked this very sort of naive-looking question, can droplets make soil? Can droplets do something very new? Is a question that material science is asking today. Chemistry is asking today. There are lots of questions associated, not just droplets, they are about micro droplets. In detail, charged micro droplets. Droplets are something that you see everywhere. Well, this form of environment is familiar to many of you. So this is bubbles. The filled form of it is droplets, and that's rain droplets, or the mist. As you cough, what comes out, the breath that you have. So all of these are droplets, aerosols, Delhi that we talked about, that's all aerosols. So is there something very exciting happening in droplets? And can we use it? So that's the question that we have been after for several years. And that has resulted in something very exciting, and that's what I wish to talk to you. Matter in confinement, like droplets, the beautiful colors that you see of rainbow and all that, has a lot to do with confinement. And that confinement, if you do electronically, electronic confinement, that's what people like Aravind Kumar and we're all working on, nanoscale materials. And they're all very important in sustainability. Catalysis, for example, Sebastian will be talking about that. Just carbon dioxide to meet methanol, for example. All of these are issues of electronic confinement. Your
automobile, cars, and how you reduce the emission, they're all to do with catalysis using confined, electronically confined materials. So this subject is very big, but I chose to talk about something very, very small in this, and this has resulted in this paper. So this is a paper that we published this year. This is a paper in a very prestigious journal called Science. Incidentally, this is the first paper in science from IIT Madras. So you can imagine how important a paper in science is. So just to give you a feel of what that is. So what did we say? We said in this paper that if you take sand, as you see here, you can actually make sand millimeter scale particles that you see outside. You can make nanometer scale particles of sand, silica, in just with droplets. Oh, what is so exciting about it? Well, this is that if you are eating rice, rice stands up because of silica. Rice stem stands up because of silica. Wheat stands up because of silica. And what kind of silica? Nanosilica. And that is why nanosilica is the most used nanoscale material in agriculture today. Is it nanoscale silica? You make it from sand? If so, you are making active soil. An active soil can bring a new revolution, similar to what our Swaminathan did. So because of all that excitement, I was fascinated by this subject, and therefore I have been working on this for about 5 years or so. And this came as an end of that, so that is this paper. So therefore I chose to talk to you about that subject. And of course, presents a large number of other questions. Can silica, if silica can be converted, how about others? Huh? So many others on the just outside. Right? We have monazite and ilmenite and everything around there. And if you just with embedded gold particles in it. So lots of business, huh? Lots of possibilities. So therefore, I chose to talk to you on this subject. So you can stop me at any that is, that's what professors do, right? Stop me anytime and we can discuss this further. Now, rocks are everywhere. And rocks make soil. We know this, right? Rocks make soil. And when a rock makes soil, soil is typically a millimeter, and that's a scale of 1,000. So a rock is typically meters. A meter is 100 centimeters or 1,000 millimeters. That's about millimeters. So the reduction in size is about a factor of 1,000, an order of 3. This reduction is what happens in millions of years. Millions of years. So this is what the giant rock is in America. This is 22 meters tall. And all these rocks eventually become soil. Is it possible to do this sufficiently fast? And that is this paper about. Before I get to that, I should give you some background to droplets. We in the laboratory have been making functional nanomaterials. Voice coming or it is? So functional nanomaterials using droplets. So if you take a micro droplet, meaning a few tens of micrometer big droplets of any solvent, it can be water, it can be alcohol, it can be chloromethane, what have you. Using these, we can make gold nanoparticles. Long ago, this is how we started, about 10 years ago. And it is possible to assemble these particles in one-dimensional fashion to give you chains. And it is possible to make this in 2 dimensions, 0-dimension particles to 1-dimension particles to do 2-dimensional sheets or 3-dimensional objects. We can create all of these in the lab, and our people have been working on this over some time, and some of these have also been commercialized. Now we also ask this question, if you take a nanoparticle of a rod, which is called a nanorod, or a spherical nanoparticle, if you put them together in a droplet, can they phase separate? Of course they phase separate. You see that these are rods and these are particles. So they phase separate, and this phase separation can be seen by spectroscopy and microscopy. This is dark field spectroscopy that we see. Particles. We do this by spectroscopy characterization of these. So all these have been going on. So I said droplets can make many, many different kinds of things. And that may be news to you, but there are several friends of mine who use droplets to make new molecules. Can we do transformations of materials? We did this experiment. So many of you will be making nanoparticles. A collection of polydispersed nanoparticles is what you have when you synthesize it chemically. And if you take these particles, suspend them in solution, and then spray them in the form of an electrospray droplet, putting this in a pipette tube, apply an electric field, and at the bottom you put a small plate, and then collect these droplets, and then what you see are these droplets coming, and eventually getting deposited, and whatever is inside these droplets get deposited. So we were so shocked and surprised when we did this experiment. These polydispersed particles suddenly became monodispersed. So on the right side, you see monodispersed particles. Fascinating. How can you have a polydispersed particle suddenly becoming monodispersed in just a few tens of microseconds, the time for the droplets take to travel from this distance, you get this. Unusual. So there are 100,000 atoms here, or 30 to 100,000 atoms in this. So several hundreds of chemical bonds are broken spontaneously to make these. So while this kind of science was going on in the laboratory, I was asking this question, hey, one chemical bond, if you make a new molecule, or you break a new molecule. Thousands of chemical bonds you break, and you do this thing. What is the limit? Can we break 1 million chemical bonds? So that took me to this question. Take a droplet, put a rock inside, and break it. Can we have millions of chemical bonds broken in a droplet? Having thought that, well, a rock has to be broken, and probably to put that into practice, I was asking a student to do this experiment. Of course, obviously, you have to ask this question, which rock to be broken? That's a crucial question, right? Rocks are plenty. So Royal Institution, if you go, or British Museum, I work in the area of arsenic minerals. How many arsenic minerals are there? Well, you go there, you will see 10,000 arsenic minerals. Okay. So this minerals variety is so diverse. Therefore, it is very important to pick the right mineral of choice. C.N.R. Rao, when he came and joined IIT Madras, IIT Bangalore, long ago, he told me, well, I decided to do some work with one instrument. That was an X-ray diffractometer, and a fascinating problem. And he chose one problem which got him to fame, and that was about phase transition of TiO2. So it is very important to pick the problem. So those of you who are young, I want to tell you that, well, it is important to break this rock, but what rock to break is a very important question. Having asked that question, I was pondering over this. So what is the rock of great significance? The rock of great significance is the rock which weathers and makes this world. Most important rock which gets weathered and makes this world is nothing but sand. And that is infinite ocean of sand. Having decided that I need to break sand, the mineral was clear to me, and that is silica. So all these are silica in different forms. So having decided that silica is what I have to break, it's very easy then get the sample of silica, and I went to a friend of mine, Manu Santhanam. He is in civil engineering department. He gave me a sample of silica. So this silica is very standard, normal silica, which is called Ennur river sand. Ennur river sand is the sand with which you study the strength of concrete. Civil engineers have to have standards. So the Ennur river sand. You can take any river sand. So having decided that this is what I need to work with, I have to put this in droplets. So if you have to put this in droplets of several tens of micrometers, I have to make these rock particles to something smaller, a micrometer scale powder of silica. So I ground it and then make this. And they look like small particles. This is under an optical micrograph. So these are 5 to 10 micrometer scale particles. And other particles are removed. Of course, you can, if you grind it, many different particles get formed. So you select these because, of course, you are doing an experiment to prove what you want to prove. You have to remove many other things, only these particles that you have. Okay, then you did this experiment. So what is this experiment then? In a simple sense, it's a tube, a tiny tube of 50 micrometer diameter, and you suspend these particles that I showed previously in water. And connect this silica tube, there is a platinum wire inside, you connect that to a potential. And at the bottom, you have somewhere here, so you put an indium tin oxide plate or a conducting aluminum sheet. So you put some sheet and ground. Between this and this, between the tip and this plate, there is an electric field, and the distance you can vary. And you, let us say, imagine that you are flowing this liquid at a small flow rate, and you collect these particles here. And let's say, imagine instead of this plate, you put a transmission electron microscopic grid. Then you can see what particles are formed. So the particle you began with is the SEM image here. Previously, I showed you optical micrograph. So you have 5 to 10 micrometer particles. But what you see, so you see each one of these particles is something like 5 to 10 nanometer particles. And what you see are these lattice spacing is that of silica. The prominent lattice spacing that you see is 010 of quartz. Other planes are also seen, but this is what you see. Oh, this is 10 to the power minus 6 microns. This is 10 to the power minus 9. So you have done this 1,000 times reduction or 3 orders of magnitude, as I just told you in the beginning. In what time scale? In about 30 milliseconds. That's the time it takes for these droplets to pass to this particular surface. Such a fast thing happens. That got interesting in this. So having asked this question that, well, you know, you can make the silica, break it down, we asked this question, is it so generic? Is it only America? At that point in time, I switched my source of mineral materials. I went to my friend who keeps a gemologist. He keeps gems. It's called Tamil Nadu, Chennai Gem Center. So he has about 140 different gems. I asked him, can you give me some gems? So he gave me some gem samples, different kinds of gems. And these are not the precious gems that you wear. These are gems that I can break, right? These are impure gems. And what you see is ruby. Took the same ruby and ground it to make into particles and sent it through that tube that I showed you. Well, again, nanoparticles. Having asked this question, okay, gems of this kind can be broken. What is ruby? Ruby is chromium-doped alumina. A tough material, that is why you are wearing it. So it means that alumina can be broken. Alumina is corundum. Can you break it? Yes, you can break it. What about synthetic alumina? You can buy synthetic alumina, and that is here. And the particles look like this. That can also be broken. So I said, natural and minerals can be broken in micro droplets in tens of milliseconds to nanoparticles. So I'm just generalizing it. All these experiments have been done. Okay. But then people won't really trust you till you have quantities of materials. In a TEM grid, a tiny picogram of material that you have, nobody is going to trust you. Somewhere in the corner of that grid, you have a particle. Don't tell me that you have done this whole thing. So you have to make macroscopic quantities. So we make macroscopic quantities. The best way to do this kind of experiment is X-ray diffraction. And that is what solid-state chemist's tool is. A nanoscale material should have wide and Bragg diffraction line. So from the width of this Bragg line, you can calculate the particle size using something called Schrerer formula. So the ground particles we put under a XRD machine, and that's what it is. These are the XRD peaks of silica. Now this powder that you collect, well, you are collecting picograms of material, as I told you, in this spray, but you can run it for hours together, days together. We collected for a month of this tiny spray and collected 100 milligrams of this and did X-ray diffraction. See, this is what you see. And that shows an average particle size of 16 nanometers. So you can convert micron scale to nanoparticles in droplets. So this is a standard JCPDS of silica. You have done the potential, right? So you vary the potential, and you see that at 3.5 kV, you have these particles. 4.5 kV, you have these optimum particles. 5 kV particles start giving all kinds of shape. And gets in. All of this is also interesting, because anisotropic particles have large surface area, and you can put more materials on top of it, such as, let us say, fertilizers. So you can put urea on top of the surfaces, which makes a nano fertilizer. So lots of interesting possibilities exist, but I'm not going to get into this aspect. So I kept this research result for some time with me. I can't publish this because I know that community will jump at me. In droplets, are you saying that rocks can be broken? Do you understand this? So I kept this with me and I was asking about what to do with it. And I have this dear friend, Umesh Wagmare, who is the president of Indian Academy of Sciences, a great computational materials scientist. And I asked him, can you do some calculations to find what is going on? So Umesh did a certain set of calculations with a student called Her name is Coendrilla. And let us say, and you break it. And you computationally break it by a cleavage. So you have this rock, and then you cleave it along one axis. Because we saw 110, you cleave it along a surface so that you can see 110. Okay, so we calculate the energy needed for cleavage from this bulk particle to this cleaved particle. We cleaved the bulk material, that is three-dimensional bulk material with three-dimensional periodicity, and material with two-dimensional periodicity, which we call slab. A bulk and a slab. And we found the cleavage energy is reduced in the slab in comparison to the bulk. So this is the cleavage energy that is plotted on the y-axis. The bulk and slab correspond to the three-dimensional and two-dimensional material, essentially to tell you that it is easier to cleave a nanomaterial. Nanoscale material, it is easier to cleave. It is to tell you that smaller the size, it is easier to break it. Very nice. But is it that only cleavage is the only way by which by material can be broken? We also did another set of calculation. So you have this material, and this material, which is, let us say, quartz, and I can slip it along one plane. Okay? Imagine I'm having this material, I can slip it over, and this is another way to break the material. So this is called cleavage. This process is essentially inducing a series of stacking faults. So this stepwise stacking fault formation, and essentially we computed that. I'm not going into details of what this process is, all that. But what we did was that the cleavage energy we calculated and the slip energy we calculated, we slip it along a particular kind of direction. You can also slip it along different directions. And I asked the question, how much of energy is needed? We found that cleavage is actually more facile, energy is lesser. But if you slip it along another direction, or another direction, energy is different. You need to slip it, but slip it along preferential directions to create this material. And in a droplet today, we know that there are many reactive particles. So if you see rainwater, as this comes down, on the droplet surface, rainwater is acidic. So we know today that. And we also know that there are many other interesting things that can happen in charged droplets, such as production of hydrogen peroxide. So many interesting things happen in droplets today, we know that. But tiny concentrations of protons exist. So we ask this question, can we have protons affecting this slip? So if you add protons, we find that the slip is affected. And we know that protons, if you add not just one proton, you can have two protons, slip is affected. So we understand that the materials can be affected by proton-induced slip. But you have applied also electric field. Can electric field do something? We can calculate how electric field affects slip, and we see that electric field also affects slip. So in summary, it is possible that particles in droplets can undergo proton-induced slip. So you might be wondering, hey, proton-induced slip and all, is it very common? You know, in metallurgy and material science, we do what is called hydrogen-induced toughening of materials. So you can cleave materials with ions, with atoms, and these are all established technologies. So proton-induced slip is very much possible, but when you start putting proton, it is also possible that the proton that is added can add on to the oxygen atom and create hydroxyl groups, and you can actually chip off pieces of silica in the form of silicate. So can you ask, you have this question, can you detect this silicate? And here you can detect this silicate in mass spectrometry. So these are mass spectra of calcium silicate, that your sodium silicate, we buy it from Aldrich. But we can also match it with the same peaks with the silicates that you get from the surface of these received particles. So we understand that materials undergo slip, but that slip also creates silicate particles. We do what is called MSMS, two-dimensional mass spectrometry, to prove what these ions are. So all those experiments have been done. But protons, I told you, on the surface of this droplet can also affect particles. So we did charged droplets without silica inside them, charged water droplets, and you sprayed it on silica particles sitting down. And we found that there can be tiny corrosion. These are the original particles. You spray this thing for a long time, you can create corrosion on the surface. So it is indeed doing something, but it is not breaking into nanoparticles. Okay. Well, I just told you, proton-induced slip happens. But proton-induced slip indeed makes this process facile, but you have to put in energy to begin with. Where is this particle getting energy? And a lot of people have asked this question, in droplets, what happens? In droplets, of course, you can have this particle, and when charges are there, kinds of sizes, the surface tension will keep the droplet together or drop together, although the charges are repelling each other. But at certain other sizes, surface tension is not enough to keep the particle together. The charges are so repelling that leads to breakage of the particle. So this is what happens in traditional electrospray. So we see, what we have written in this paper is that at certain stage of this particle breakage, these micron-sized particles also break down to lead to nanoparticles. But we don't know what exactly is going on at that time. This subject has been debated quite some time, not only by me, people as well as Lord Calais. If you have a droplet, and the droplet is, let us say, breaking, at that point of droplet breakage, it is possible that there can be big pressure fluctuations inside. And the pressure fluctuations inside this can be as strong as something like 100 megapascals. And this kind of enormous pressure fluctuations can set in changes in a particle that is inside and result in particles breakage. This is assisted by proton-induced slip as well, is what we think is happening in materials. In addition, when you have droplets of this kind, it is possible that on the surface you have a different concentration than in the bulk, as I told you in the beginning. So this kind of partitioning is possible. Surface, there are new species like hydroxyl ions, hydroxyl radicals, protons, H2O2. There can be interesting chemical reactivity. There can be surfactant defects. Many of you know, if you of that kind of dimensions, there is species come to the surface because of surfactancy. As the particle moves, evaporates, this is not working. Solvent evaporates, and then the droplet size decreases, and the decreased droplet size can result in interesting reactivity for species inside. All of these people have studied. So a composite of many, many interesting things can happen, and all of this is likely to happen, and someone has written a perspective on this, what is actually could be happening in the droplets. An interesting thing what is happening in these droplets could be that in the droplets, in presence of CO2, in presence of nitrogen, there can be new chemistry that is happening on the nascent surfaces that are being born. Nascent meaning the virgin surfaces of silica that are being born. So this takes me to a very interesting question. As the droplets are coming, these particles are breaking, can I really capture this? So currently, we are doing this experiment. As this is coming out, at some point we capture these particles and ask this question, a single micron scale particle, can I see its breakage? Now this is like in situ spectroscopy, mass and microscopy, how it is happening. Today we don't know it really, but this is an effort that is going on. It's told you that everything can be broken. So is it possible that graphene can be broken or molybdenum sulfide can be broken? Yes, these are molybdenum sulfide sheets which are broken to nanoparticles. We are just writing a paper on this particular thing. How about graphene? Yes, it can be broken. So these are all industrial products. By the way. So these are technology if we wish to. So can you characterize it? You can do all these spectroscopy, Raman, etc. That we can do. So I just told you one side of this story to tell you that interesting material science is happening right here in droplets. Very, very normal things that you see, you and I see every day under your shower. Okay? Very interesting new science is being born. What is this good for? So to tell you what is this good for, I should take you to another direction. So this is another kind of materials we work on. So these are called atomically precise clusters. So these are a few atom clusters. This was 25 atom clusters of gold and silver and platinum and palladium and many things that we work on. Not just 25, we make 20, 30, 50, 100, all kinds of things, but atomically precise. You know, you have heard about 6H6, right? Similar to that, can I have a new molecule? Yes, we make new molecules of that kind. And this is one such example. So on the surface, there are ligands that you see. And this is something that we have been working on for many, many years now. And I must have talked about it in different places. Some of you must have heard it. But what are the new things? The new things, there's many, many new things. This is a book that I have done last year on this topic, and I have a Gordon Research Conference that I have conducted. So this is a subject which is expanding. We have written special issues in accounts of chemical research, JACS, and all that. Okay, so this is a paper done by one of my students. I just wanted to show you something very new that is happening in this area. So this is by this boy, who is a PMRF fellow, and it's just in the revised form it has gone. So what did he do? He took a new ligand. So this is something of you must have heard about called carborane. Carborane are this kind of entities. These are boron atoms, and these are two carbon atoms. A very familiar person to many of you, Professor Jemis, works on this kind of boron systems, boron cluster systems that you know. Imagine you make a ligand out of that. So this is a sulfur added to that on carbon. So he just took this. There are many, many different kinds of things that you can think about, many different isomers of this kinds of systems, many different places this carbon can be put. This is orthocarborane. I have metacarborane. I have different kinds of carborane systems. We work on many, many different things. Imagine this is what it is. Okay? So this boy made a new cluster. You see? This is 17 atoms of silver with 17 atoms of silver. The shape is tetrahedral with 12 carborane sitting around. You see, at the center there is an atom. So he decided to change that central atom. So there is a central atom, and there are 12 atoms outside, and then 4 atoms. That makes 1 plus 12, 13, 13 plus 4, 17, and that is what this structure is. He decided to change the central atom, and that he made it gold, silver 16. Huh? Beautiful. And then he decided to change these 4 atoms on the surface and Cu4 Ag13. He changed both the inside and outside. Four coppers outside, and rest of it is silver. Beautiful. Beautiful. You just have to go and just shake something and then get this. Okay? Now all of the 3 or 4 of them. So he makes these. So what are these things good for? Lots of interesting things they are for. And they are packing in different ways. And they form very interesting porosity, beautiful structures. And I'm particularly interested in water. So they are so interesting that they make beautiful emission, very intense. And when they are so intense, you ask this question, are they good for something? Yes, they are good for, they are useful to detect contaminants in water. So we make sensors out of this. And today we can detect even 1 part per billion of arsenic in water, right from tap water, right from well water, without any pre-concentration, you can detect. With atomically precise clusters. Why this Vivek's cluster is interesting because these materials in general are metastable. And they are really not very good in the laboratory for commercial applications and all that. But these materials, although they are clusters, they are stable up to 370 degrees centigrade. Which means that you can utilize these properties very well. So, I work on water, right? Water microdroplet is what I just told you before. By the way, I should tell you that silicon does not break in methanol, ethanol, and all that. It only breaks in water. The other side of my laboratory, we work on clean water. And this is a paper wherein we made composite materials, porous composite materials to remove contaminants from water and make clean water. And this is now a big effort nationally. And so if you have a water treatment plant, let's say storage vessel, which is supplying water to 2,500 people, let us say, in case the water has a contaminant, we have introduced a filtration methodology using nanoparticles. And this removes arsenic and uranium and cadmium and mercury and all that. And you get clean water. And today, we have 1,700 of these community units across different parts of the country. So it's a massive effort that goes on. So in the laboratory, we make materials to new kinds of devices and then implement them in the field. This is a kind of technology that I just told you, which is in different, larger form, is the commercial community water purifier. But there are other technologies that we work on, desalination and atmospheric water capture and things like that. But we also do sensors. We evaluate water quality in different parts of India using sensors we have developed. And today, this is a private website. I mean, people cannot see it today. So we monitor this. Not only us, many different organizations are Expand on this, this is what you see. And each one of these data points, you get water quality data. One student, if the person is doing 10 water sources analyzed, 100,000 students can do 1 million data points. And our objective is to do 100 million data points using this analysis. With that, we will develop big data on water and understand water, what limits clean water to people, and what are the parameters which limit clean water to people by using artificial intelligence. All that introduction I just told you, connecting to what I just told you. I told you that droplets are there in rain. And these droplets might be breaking minerals. And in those broken minerals, new chemistry is being born. And some of that chemistry could be the chemistry of relevance to biology. Carbon-nitrogen bonds and carbon-oxygen bonds and what have you. And if you can understand this, we will be understanding new processes. At the same time, the droplets which are making minerals will be probably producing rich soil. And if it is true, it is possible to do this, that sand can be converted to active minerals using water. Of course, water is not available, but water is available in the form of wastewater from these cities. Use water for activities such as this, which will mean that you boom. So making soil using processed wastewater to address this world food crisis is a very important problem. So what I just told you is natural minerals break spontaneously in charged water microdroplets. It occurs only in water so far, and not in ethanol. And that probably is telling us a very important message. Studies on a variety of materials we have done. It is facile due to proton in slip. It is detailed investigations that are essential to understand what exactly is happening, and implications to the production of specific minerals is very, very important. So there is a new category. This is what I just told you, by and large. And there is a new category of materials called atomically precise clusters, and that is just evolving right now, very fascinating. And carbon thiol protect new clusters to this family of materials which are beautiful, which are structurally beautiful, stable, and they are also light emitting or fluorescent in nature. I also told you that clean water can be provided with advanced materials. I showed you a tip of that large iceberg, and technologies based on them are currently used in the country, and they are being promoted by Jal Jeevan Mission. And if you look at Jal Jeevan website, you see these approved technologies. This kind of science is also telling us that water is fascinating. So today, water can be observed. Water can be seen by microscopy. So this is our new microscopy center. We have just set it up. And this is called the National Cryo-Electron Microscopy Center. And with that, in that we have cryo-electron microscopes. So cryo-electron microscopy won the 2017 Nobel Prize in chemistry. And this is nothing but frozen water sample in which you can put molecules like proteins and understand the native conformation structures of biomolecules, even viruses and such things. So COVID, just after COVID was detected, in 6 months we had vaccine, because cryo-electron microscopy could solve the structure of protein virus. It was impossible. The virus structure would have taken tens of years before, but today it is possible to study this using cryo-electron microscopy and come up with structures. But it can also be used for many other things, such as lithium-ion batteries and advanced materials and what have you. Many, many interesting topics. So I wanted to use these for clusters. I wanted to use this for water. So today we have set up this facility. There are 2 microscopes here, and this is a 50 crore research facility. And there's one more microscope which you are not seeing. And today, this microscope, with that microscope, you can see water. So these are water molecules. And this is not from our work. In frozen water is what you see here. And this is cubic water, unlike the regular water, which is hexagonal. But you can understand has such structures. Our objective is to understand how water flows through membranes. And this will, of course, result in new kinds of understanding of purification devices. Well, it is also being understood. Today, the topic that I just told you about, minerals being broken, we study that subject also using this kind of microscopes. The subject of water is so big. And I have been in a position to take water technologies built in the laboratory to field. But that was a very, very strenuous job. But many people across the country are building water technologies. But they are not in a position to translate those technologies to field because the connection is lab to field connection. There are many things that you have to build, technology translation. They are not available. So we built a new center called the International Center for Clean Water. It's a 22,000 square feet research facility on water. Anyone can come with an idea on water, build a technology, build a product, and walk out. IIT will not take anything from that. So this is the International Center for Clean Water. And the science that I just told you was done by one student, largely, and that is Pooty. So this is that paper, and she finished her PhD. She is now a postdoc in Purdue University. He won the Best Thesis Award by Madras. I showed you the work of another boy, Vivek. So he is continuing his work. There are many others and many other activities in the group which I did not talk about. The work was done in collaboration with who computed these with Cointula, whose picture is not shown here. The last number of collaborators across the world, I collaborate with 27 countries, different activities. Different things go on, and you see different nationalities here. I should tell you that the science of this kind happens just because of students who are committed to translating something. And this happens because in an institution like IIT, where students get a job in the 4th year, if they're BTech, they get jobs in Microsoft, they get jobs in whatever companies. But instead of going to those companies, they chose to work on an idea in a startup. And that is essentially because parents trusted in the technology, parents trusted the students' capability to build something new. And this happened, and this is a changing IIT, where many students choose to work on new ideas and emerging ideas. But then this also happened because of institutional freedom. Tremendous support from this institution called Department of Science and Technology. These days, the kind of science that I told you, the cryo-EM and all that, is because of the new support that we have in Institute of Eminence. I got funding from the Department of Science and Technology. IOEM, balance money, a portion of so this is also it is also possible that sciences of this kind became possible, or the water that I told you about in briefly, because in those years money was not there. Many people came and gave me a small check. Hey, this we believe that you are doing good. Take it. Maybe of use to you, some of you. I was so upset that nothing was going on, no money was available. One day I was giving a lecture. I told somebody, hey, I need some money. He asked me, give me one page. And 7 days later, I got 30 lakhs of rupees. This is how this country is. It's also very important that a lot of passionate people outside, they just have to see a passionate individual. And it does happen. My science happened also because of these people, many outstanding individuals who had, generosity. And this great institution, we keep publishing in many, many different places. This is this year's many cover pages, and these are 2 of them. A great institution. I should tell you, one of my directors was the previous director. So I write these agreements on behalf of the institute to give clean water to this district. And he one day asked me, Pradeep, you just came back signing this document to say that we will give clean water to that district. Are you putting IIT at risk? You are just 4 or 5 of your students to say that we will provide clean water to people. How sure are you? Aren't we at risk? I told him that, Bhaskar, do you know, if you go to San Jose, the whole San Jose, San Francisco, San Jose, is all IITs. What did you produce? You produce these kids in San Jose, don't you? Bhaskar kept quiet. So my institution kept quiet. And so that and supported whatever that we do, a great institution. And I turned 60. So last year I turned 60. So people asked me, my own people asked me, hey, what is this great learning that you have? And this is a message also. To me, the great message was that institution enabled everything, but what was the single most important thing that institution gave? And I used to say that the most important thing institution gave was freedom. Just freedom. And that if you, many people, far more, and this generation is poised to do greater things in the years ahead. Thank you very much. I have a lot of time left for questions.
Okay, that was really an enlightening talk. Now I invite Dr. Franklin John, Vice Principal of Sacred Heart College, Thevara, to handle the session. He is currently the visiting scientist at Weizmann Institute of Science in Israel. He is the recipient of the Kairali Award in 2020. Sir, please.
Thank you. Thank you, sir. Let's congratulate the pride of our nation, Professor T. Pradeep again. This kind of research, which he is excelling in, is something what I have witnessed a few months back while I was there at Weizmann Institute, where I have seen on one day when my mentor, Professor Ada Yonath, was sitting in her office, and 2 guests came from United States, 2 Jewish people. They just came to donate her billions of dollars to recognize the contribution. So I was just thinking in my mind, will that happen in India? And that's what Professor Pradeep was mentioning. It's so incredible, sir. And thank you so much. Thank you so much with your presence here for our conference. I got fortunate to visit some of the farms in Israel where they have converted a desert to a fertile land. So they have introduced a technology called Inaugural for creating fertile soil. This kind of research, where translational research which converts science to daily life is incredible. And with that, the floor is open, and I invite questions from the audience because this is an opportunity to interact and ask your questions and queries. Please.
Professor Pradeep, it was really fascinating to know. I had missed this article. And it's really very interesting to really identify the mechanism of this fracture. But one thing that comes to my mind is this reactions, chemical reactions under nano confinement has been going on for 5-7 years. It's relatively new. So the extra energy actually comes from the surface energy. But here you talked about that Coulomb thing. I mean, you have a highly charged state. Some kind of a Coulomb explosion that happens in hot atom chemistry that we talk about. Something like that is happening. Right. Because that through, and also, what is the mechanism? In electrospray mass spectrometry, we very commonly hear. What is the mechanism of breaking of molecules? That allows us to do the mass spectrometry instead of.
Yes.
So maybe there is some linkage.
Absolutely.
Yeah, some linkage to that.
Yeah. So Coulomb fission, or the Coulombic repulsion, which overcomes surface tension, at that point things break. But that breakage and the next few, let us say, microseconds, what all the events that are happening in that droplet, we have not really captured. We have made a lot of attempts. People have done fast time resolved spectroscopy in this context, but could not resolve this very well. So computation is a way forward in this direction, but the dimensions are so large to understand this whole system. So that is where another limitation lies. But one thing that we know from computation is what happens to the pressure fluctuations inside. But how these pressure fluctuations affect the particle inside has to be now studied. And that too should be investigated with spectroscopy. So I've just started investigating this. I don't have data to tell you as to what actually happens at that kind of pressure conditions. Do we emit light? So there is sonoluminescence there that people are aware of. Is it possible that under that breakage you have the energy that is breaking? Is it producing also excited atoms to give you X-rays? So lots of interesting science we are beginning to explore. I don't have yet data. Yeah.
The only thing, which is doing the trick is the only difference between the other solvents and water is these have got a dipole moment.
Absolutely.
So there is some connection.
Yes. Yes. So something is unique in water.
It's very interesting.
Yes.
Thank you, sir.
Good morning, sir. I have a couple of concerns. My first concern is the formation of the nanoparticles during the electrospray. Can I make that formation of these nanoparticles when I provide some other stimuli other than this electric potential? Using some other stimuli, can I induce the formation of the conversion of these microparticles to nanoparticles?
So far, micron scale particles to nanoscale particles in droplets, we have so far gotten with electric field only. However, micron scale particles have broken chemical bonds, single bonds, a few bonds, with other stimuli such as pressure. So taking that further, can I have a very high pressure doing this process? Of course, droplet itself is under pressure, called Laplace pressure. But that is not very large. Is it possible to create 200,000 bar inside? Then it is possible probably to create this. So how do you create it? Is a question. So there may be other processes of cavitation that you can do. So I know today, this is one way of doing cavitation. Well, is it possible to do ultrasound? Another way of doing that. Is it possible that, I told you charges that are given, but is it possible to give charges not only by electric charges of this kind, but ionic charges? I told you protons do this, but can I not put sodium chloride? Then it becomes seawater. Is it possible to do? So those are interesting directions, but can be done. It can be done. But these are the possible stimuli that we can do. Pressure, cavitation, ultrasound, and maybe other ions.
So then my second concern is can I intuitively image the formation of my nanoparticles?
This is the effort that we are on right now, but we are doing this, collecting it and putting it in the microscope at various stages. This is what we can do. Microscopy depends on scattering, right? Anything, electron or whatever, something has to scatter from that thing. And in an ambient atmosphere, you can't do electron scattering because electrons have to be produced. So you can only do optical scattering. Optical scattering, if you do optical scattering, your dimensions have to be, you have to do X-rays to see that. So those are the limitations in this, but that is also an effort that has to happen.
So my last concern is the extension of the previous question. So the formation of these nanoparticles happens only after the deposition as a film or during the course of the passage itself?
They are being born at that time, and that's what you're capturing and then measuring. Okay. Not on the there. So they are not hitting and doing it.
Okay.
In the droplet it is happening.
Thank you, sir. It was nice to hear from you.
I request the postgraduate students. Please.
Hi, sir. I'm Anu from JNCSR Bangalore.
Very nice.
So first of all, it was a great talk.
Thank you.
So I would like to know about the mechanism of that silver-based cluster. How does it act as a contaminant detector?
Great. So at the nanoscale, let's say this 1 nanometer or below 1 nanometer kind of dimensions, they have states which are similar to molecules, and those states are due to certain kinds of surface bonding structure. And anything that can interact with those, the electronic state will change. So our luminescence can change, can shift, whatever. So this is what happens in this material. And they are, because of the surface structure is such that only specific ions interact or specific molecules interact, so there is analyte selectivity. So coming to the key issue is surface electronic structure, which is influenced by the geometric structure. And the readout can be luminescence. Readout can also be cyclic voltammetry kind of changes in the oxidation reduction potentials. It's also possible that optical absorption spectroscopy can be used, but sensitivity is substantially lower. So we depend on luminescence as the principal readout.
Sir, another thing, in that nanoparticle formation, does the size of that droplet matters?
Yes. It is only in this kind of size regime, that is a few tens of microns, the nanoparticles are formed. Now at a smaller dimension, people know that in droplets you can go even up to 300 nanometers. People have detected such droplets. So where exactly this process is happening? Typically in the micrometer to nanometer regime it happens. Beyond 100 nanometers, nothing happens. So that is where it is almost like bulk. So, but then the very specific narrow regime has not been resolved.
Okay, thank you, sir.
Yes.
So I request the postgraduate students to come up with few queries. Yes, please.
Yes. Yes, I know.
And sir, my concern was about that you said that from the tip of that microtube that microdroplets are coming and the monodispersed nanoparticles have been captured. But my question is how these nanoparticles are captured. I mean, like, I was curious to know how these things are happening or how these nanoparticles are being captured.
Fantastic. So let's say imagine if you have breath. Breath has droplets. How do you capture droplets? Put something in front of it and condense this droplet. So if you collect all of them, typically what you do is you cool the condensing surface. Let's say liquid nitrogen, condense the whole thing. But in our kind of experiment, droplets are coming from the top, and these droplets are having nanoparticles which are having higher densities. And they don't normally fly away, they get deposited due to gravity. Okay? Gravity can act on these larger droplets. Nanoparticles, they may not, but larger particles, they do. Now, we also apply an electric field. This is, let us say, negatively charged, high negative potential. This is ground potential. So when they are accelerated towards the ground. So all the particles are getting collected on the ground because of electric field also. Now, in case if you wish to collect everything, you can also cool the surface to collect everything on the surface. But we don't have to do it as far as this is concerned. To go a little further, we may be missing a few particles, because the particles may go on, a few of them, but that loss is much less, just a few percent. So 100 milligrams we wanted to collect, we collected nearly all of that. Okay.
Sir, all these nanoparticles are same coming from that tube?
Meaning they are similar in size. You saw in the TEM micrograph, they are similar in size. They are not the same, similar. Small differences exist.
Is that physical properties being same or?
So that kind of sizes, like polymers, you must have studied polymers. There is a polydispersity in polymers. The number polydispersity and all that you would have studied. So in a polymer, monomer number is within a range. Small changes happen, but properties are roughly the same. Melting point, they don't call it melting point, they call it, they are softening at a given particular temperature, polymers. So this kind of properties are essentially similar. A given nanoparticle may be, let us say, 10 plus minus 1 nanometer. So it can be 9 or 11. So there is that kind of variation.
Glad, sir. Nice to hear from you. Thank you.
Anyone else? Please.
And is there any concern of toxicity in this regard?
So question is, I talked about cleaning materials, water with nanoparticles. Is there a concern of toxicity is Dr. Grace's question. So nanotoxicity has been intensely evaluated in this subject area. And the key concern is whether nanoparticles are released in water. And we spent quite a bit of time evaluating that. And so we understood that if the nanoparticles are anchored on surfaces at sufficiently good strength, they don't get released into the environment, into water. And so in the early stages of this work, about 20 years ago, nanotoxicity was a concern. And we do have many materials which release nanoparticles, and therefore they have been stopped also. These materials are nanostructured materials. They are not nanoparticles. They are nanostructured materials, just like TiO2 that you have. So this is what has happened and what has really resulted in their implementation in the field. Lots of experiments have happened, whether there is any nanoparticle release at all. If at all nanoparticle release is there, whether bacteria or human cells and plant cells, animal cells pick up those particles, yes, all of those studies have also happened with our materials. So sum and substance is that they don't release nanomaterials, and therefore there is no nanotoxicity associated with it. So it is now Government of India tender documents have this. So I have been insisting on putting nanotoxicity in the tender documents. So all those have happened.
Thank you. Anyone else? Please.
Please think about the next few questions out, right?
Good afternoon, sir. My name is Anupama. I'm from Central University of Tamil Nadu. Sir, my question is that this kind of spontaneous formation of nanoparticles in the micro droplets, we are trying to study this because we want to understand the weathering processes that is happening in nature, because charged aerosols are being found in nature. So how close are you in mimicking the kind of natural conditions present in our atmosphere using this electro-spraying technique? So only if we are able to mimic that kind of aerosols present in nature, we have to study that weathering process better, right? So how close are we in studying that?
Yeah. All I talked about in this lecture are studies that are laboratory studies.
Yes.
Wherein I am particularly interested in a phenomenon, whether it occurs or.
Yes, sir.
Now, how do I take it to the field? Just as previously I was talking about, I talked about a synthetic methodology to create materials. I put it doing this. Now I'm not making 1 milligram, I'm making 100 parts. So process is different. But the phenomenon I have understood. So similarly, this process is understood, phenomenon is understood, therefore I can take this field of relevance. So how do I? Imagine I have rain, a new kind of rain, with droplets that I produce. Typical rain is not just these droplets or many other things. Droplets alone I produce. And we use these droplets in the form of, let us say, coffee drying. Instant coffee. How are you making? Droplet dry? How are you making milk powder? So we have industrial processes where we have a very high pressure. I can't tell you more about it because I want to make money out of that.
Okay, thank you, sir.
Anyone else, please?
Yeah.
Good afternoon, sir. So my question is like in M17 nano clusters, particularly you said that gold silver nano cluster, due to its light emitting property, we can detect the contaminants in water.
Yes.
So is there any other application due to its light emitting property?
Of course, there are many, many properties. For example, this person who has just come in, his name is Sebastian Peter. He's going to give you a talk, and he uses this kind of material for catalysis. So many properties are there. There are others who use it for thermoelectrics. So every property that you see is electronic. So I keep telling in my classroom that what I see are this magic of electrons. So this is true of nanoparticles. So many, many electronic properties. And one such is catalysis. I told you about luminescence. This is one such property. Okay. Here there is a question, and you have a question here? Okay.
Yes, please.
Yeah.
I mean, I could not, can you give me more detail about that?
So I said that when Professor Umesh Wagmare calculated this, how can particles be broken in a droplet, he essentially calculated energy is required for two different types of processes to produce smaller particles from larger particles. One is essentially to break a crystal. That's called cleavage. So cleavage is nothing but inducing in a given crystallographic axis, you keep separating two layers. Another way of separating this particle is by slipping. So you keep doing one step at a time, an atom is shifted or slipped. So this is a series of dislocations that you produce. And that is one way. This is another way. And this we calculated, we found that this is possible. This also we calculated, we found that this is possible, but we found that this is even more facile in presence of protons. So that's why we call this as a proton-induced slip.
That may be energy of two different configurations. Maybe.
Correct, it is certainly. Now, of course, this can, there are other ways of looking at it. The two particles that are formed, they're also surfaces functionalized. In water, they're functionalized with hydroxyl groups. That functionalization, of course, releases energy. This energy can be used for breakage. So the net energy required is small. Only just that there is an activation barrier that is required. That activation is what I told you by the kind of pressure fluctuations that happens. So overall, the system is going to a thermodynamically minimum form because the silica, that surface that got formed, is hydroxylated. For any material surface that's formed in water, is hydroxylated.
Anyone else, please?
Yes, madam.
Hello, sir. Myself, Riya. So you formed a cluster and you incorporated gold and copper into it. So does the cluster without these metals and all those clusters with these changes, do they vary in their sensing capacities? And why gold and copper?
Of course they do change in their capacity. Every material that I just told you about, they're all different in their electronic structure. So I told you about this material. I told you about this material. And I told you about this material. And I told you about all these four different types of things. There are four different types of clusters. They all have different types of electronic structures. They all have different kinds of metals because they're electronic structures. Their ionization potential is different. So depending on what I'm using, let's say I'm using the luminescence. What? This luminescence for A, B, C are different. Because their structure is different. Because their bonding is different. Because their interaction with arsenic is different. So the luminescence change that we have is also different. Some clusters might be better than others. And we ask this question why? Then we go ahead and compute this. What structure enables that? Because it is difficult to understand this detail just from solution. In some other cases, just as organic chemistry you might have studied, let us say if you're at a transition state, is it possible to understand the transition state by mass spectrometry, NMR, or sometimes even by X-ray diffraction? We do. So in cases where we understand completely, we do have this kind of structural understanding. Structural understanding leads to understanding. You know about the properties.
So why gold and copper is there in specificity?
7G, that I told you to begin with, we don't have gold 7G yet. We don't have it. Why we don't know? It must be possible. It has to be explored to create conditions, and it is certainly easy. This is true of other materials. Some years ago, we used to think that why only is gold, silver, copper, why not iron? I just got a paper. Clusters with iron. Tomorrow, people will make all of these. So I'll be a fool to say that nothing is will be possible. It's just that the right conditions have to be found, and etc.
Thank you, sir.
Okay, since we are running out of time, let's conclude this session, and Professor Pradeep will be available here. So let's all join together to once again acknowledge the pride of our nation, Padma Shri, Professor Pradeep. Thank you, sir. Thank you so much.
Thank you.
I express my sincere gratitude to Professor T. Pradeep for the lecture. Also, I would like to extend my gratitude to Professor C.T. Aravind Kumar and Dr. Franklin John for chairing the session. Thank you all for your time and attention. Some announcements. All the participants are requested to mark their attendance. Attendance sheets will be provided outside the Malicious Hall. The oral presentations on the topics organic chemistry, chemical biology, and applied materials and interfaces will begin at sharp 1:30 p.m. in the Physics Seminar Hall on the first floor. Those who have mailed the presentations for the oral presentation competition are not required to hand over their pen drives. The participants of the poster presentation competition are requested to hang their posters in the respective poster boards near the Department of Chemistry, and the valuation of the same will begin at 3 p.m. For more information and help, kindly contact our volunteers. With this, there is an end to our morning session. Now I request all the participants to gather at the Marian Hall for lunch. Volunteers will lead you to the venue. I request all the delegates and participants to gather at Malicious Hall at sharp 1:30 p.m. so that we can continue our sessions without delay. A gentle reminder, all the participants are requested to mark their attendance. Attendance sheets will be provided outside the Malicious Hall. We will adjourn for lunch at this time. Kindly return at 1:30 p.m. for the second plenary lecture by Professor Sebastian C. Peter. Thank you.
അല്ല വേണ്ട 4 വണ്ടിയുണ്ട്.
Now, we are moving on to a second plenary lecture by Professor Sebastian C. Peter from Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru, on the topic titled Carbon and Water Recycling for Sustainable Energy, a Journey from Fundamental Chemistry to Green Technologies. I am indeed honored to introduce the chair of the session, Professor N. Manoj, Professor at Department of Applied Chemistry, Cochin University of Science and Technology, and University Coordinator of RUSA scheme at MHRD at CUSAT. His areas of research include chemistry of reactive oxygen species, organic synthesis, photochemistry, photophysics, and photobiology. I kindly invite you, sir, to chair the session.
Wish you all a warm afternoon. Please be awake for an enlightening lecture on a theme that all of us are interested to listen to. And I am privileged to introduce Dr. Sebastian C. Peter, who is our alumni. I am proud to say that he is our alumni from the Department of Applied Chemistry, Cochin University of Science and Technology. I think he was introduced to the world of catalysis there from the department. We had this former course on MTech in industrial catalysis, and you were in the first batch, the third batch of this program. And he is one among the most accomplished alumni of our department, and we are always proud to say about him in anywhere and in any forum. Dr. Sebastian C. Peter is currently a professor at the Jawaharlal Nehru Center for Advanced Scientific Research, JNCSR at Bangalore. But I would like to mention him as an entrepreneur, and he owns his own startup, and he works in the development of catalysts. Am I right? Yeah. And beneficiation or mitigation of CO2 and its conversion to beneficial chemical products. So this is many researchers who wish to become owners of their own company, and his company has become one of the most noted companies in the domain of carbon dioxide utilization and conversion. So his early research career spans from a PhD from University of Münster in Germany, and later he did several postdocs and started his teaching career at JNCSR in the year 2010. And from then on, he is an avid researcher and a good teacher, and he has won several awards, including Chemical Research Society Award and Material Research Society, and several international prizes also. And his startup company has scaled up a technology to convert carbon dioxide to methanol from a lab level to a capacity of 300 kg CO2 per day. And is one of his noted achievements in this domain. And his startup has been selected for the Rajiv Goyal Prize in 2024 this year. And he is funded heavily by industry as well as government agencies. But during an after lunch session, he said, no, I prefer to get money from industry, and most of the industry are now approaching him with enough funds to drive his research in a very important area. I welcome Professor Sebastian C. Peter to deliver the lecture entitled Carbon and Water Recycling for Sustainable Energy, a journey from fundamental chemistry to green technologies. Over to you. Thank you. Can you hear me?
Yeah, I am overwhelmed with that long introduction. You took almost 10 minutes from my time. Okay, I will try to patch it up. Yeah, so first of all, I would like to thank SSC Thevara, particularly Ginu George, for the kind invitation. And happy to be here for the first time, although I roam around this part of the world of 2 years during the CUSAT time. So never been this part of the world. So happy to be here. Well, I just come to the topic, carbon and water recycling. Two important problems. Currently, we talk all the places, whether you take it social media, scientific forum, political forums. So these are the topics we talk about. Even the inaugural section, you might have noticed that one. All the speakers talking about the carbon related work, CO2 capture, CO2 utilization. Professor Pradeep was talking about cement, say for example. And then CO2, what you call food, say for example. In fact, we also produce acetic acid is a kind of a food. So this kind of, subjects, at various platforms discussing, and then I will try to bring, the journey we had. Why I'm giving this talk as a journey, you are all young minds, younger minds of this country. Probably Professor Pradhaban knows me younger days, and my another beloved professor, yes, Paulson Matthews. So he started the career teaching me, and he is sitting there. So they know me how, Sebastian at that time. So the journey was actually some kind of a different path. So this is a kind of inspiration talk to you. What I could achieve, with all this, scientific contribution. So, how to move? This one, huh?
Yeah.
No? That is the concept. Yeah. So you just fix that one by the time. So, well, if you look at this figure, we are, depending, this is all the resources, oil, gas or natural gas. Whatever you use daily life, most of the items, or I would say, all of them can be produced from oil. If you look at this figure. And if you look at this side, energy sources, and so oil extensively used as energy fuel. So it can be used as a potential for the production and the energy also. And if you continue the next slide, please enter. If you look at this one, the energy demand. So if you projected this energy demand, by 2040 in British thermal units, around 250, 240, 250 from petroleum, natural gas is increasing. Coal is a kind of saturated because most of the coal plants all over the world shut down. And then you can see that renewables growing day by day. Nuclear is a kind of settled down because no more nuclear plants are coming. And then, this is increasing day by day. What happened? Yeah. And each process, whatever the process, so you're basically burn carbons. If you look at the first equations, you're burning coal and you produce an energy. And during the process, you are producing carbon dioxide. Or if you take methane, There are also energy production, but carbon dioxide. If you take in a heavy hydrocarbons like diesel, petrol, other gasolines also, you can see that one equivalent amount of CO2 is producing, whatever the number of carbon dioxide. And during this process, you can see that by 2022, this is the diagram, 5.1 gigaton of CO2 we are dumping to the atmosphere. This also contribute a huge amount by the deforestation, because naturally built forest is actually not taking care about the natural source of CO2. And now this number is something around 6 plus gigaton CO2. Staging? Okay. So if you look at this figure, cartonic image, you can see that last 1.5 century, the temperature is increasing because of the amount of CO2 that is depositing. So from below to 300, now we are around 400 ppm, and the temperature is risen by another 2 degrees. And all these resources, all the sources like stationary sources like electric power plants and power producers, independent power producers, manufacturing plants like cement, limestone, hydrogen, production, ammonia, etc., etc., and mobile sources also. All the sources actually producing large amount of CO2. We have also natural resources, you can see that, but that is taken care by the nature itself. All this area, the first 2 columns corresponding to the human-made, human creation. All we are responsible. Okay, so for example, daily we are using our automobile, you are using your computer, you are using your mobile, anything you can talk about. I used to give one example, most of the talks. Say for example, every day morning the first activity what we do when you get up from the bed? Look at the mobile, including me also. Mobile is the first one, and you look at which email or WhatsApp message, right? And you reply to that WhatsApp message. Somebody say hello, you back hello. How are you? How are you? And then it depends on how much you use that mobile. At the end of the day, you charge it, right? And nowadays, reels are very common. If you open Facebook, you will take into one reel, that will drag to other reel. Depends on your interest. That automatically AI created in such a way based on the interest that drag you. And then it's a kind of addict actually. It is not a smoking or drinking and nowadays addict. It's actually the social media is actually kind of addict. And depends on how extensively you use that one. You may charge it 2 times, 3 times in a day. But this electricity is coming from some coal power plant. They are burning carbon. And you are one high equivalent to one CO2 molecule. Okay? So one carbon is equivalent to, one CO2 is equivalent to one high. It depends on 100 highs, 100 carbon dioxide. So you unknowingly you are contributing the CO2 deposition. What happened? It's okay, fine. To remove now. In Hawaii, they measure that average CO2 all over the world and calculate. You can see that in June 25, 2024, around 427 ppm. And 1 year before, it was 5 ppm lesser than that one. Just calculate every year 5 ppm. In 10 years, 50 ppm. 20 years, 100 ppm. By 2050, it is going to be around 600 ppm. Today morning we heard that one Delhi city, Professor K.V. Thomas, he was mentioning about, he want to run away from the Delhi city because of the pollution. And the whole, education system is actually shut down, they can do the online classes. So that 600 ppm, that is the equivalent average CO2 level by 2050. And interestingly, there is a study done by International Panel on Climate Change. If you look at that, the shaded area, it's going to be underwater by 2050. Okay? Our city, Kochi, is going to be underwater by 2050, like Dwaraka. We will not see this city if we continue this way. That's kind of a scenario we are at this moment. I forget about this figure. And if you look at this one, depends on the percentage of CO2 in air, 1%. You can see that when it ends up in drowsiness, 3%, your hearing ability will be reduced, or increased heart attack, heart rate, or pressure, or even mild narcosis, or if you continue, more, 5% of dizziness, confusion, headache, and if it is more than that one, end up in losing your life. But if it is 1%, slowly that is affecting your body without immediate effect, probably after 10 years or 20 years or 30 years, it will affect your body. Okay, so you are basically slowly dying because of this pollution. And there was a statement from President Barack Obama in 2014-13, at that period, the pollution is actually majorly because of India and China. Many people criticize. Actually, the fact was, appreciating when these two countries were developing at that stage. And if you look at closely, 2000, you can see that one, that the contribution from China is a kind of exponential growth. India slowly built, both are related to GDP. How good GDP, more amount of CO2 is actually dumping. More GDP, more development, more industrial revolutions, or our urbanization, whatever you can think about. For example, Kochi city, Professor Pradhan can mention that one maybe 25 years or 30 years how it was, right? It is completely different. And the same thing, if you come to Bangalore, our city, that's the worst in the world in terms of traffic. Recently, one Facebook or some social media, in a very interesting way. So, if you want to cross one side of Russia to other side, you need 149 hours. In a joking reply, you don't have to go to Russia, you just come to Bangalore. Okay, so the traffic is so huge, and then it is actually filled with full of cars, and then automatically the city is in a very bad situation. There are certain technical terms. Carbon neutral, that is equal to, that defined carbon emissions equal to carbon removal, or net zero contributions to carbon, net zero emissions, carbon negative removal of carbon from the atmosphere. These are the technical terms used to see on regular basis. I may also come later. To make it a net zero, along with other countries, in COP26, Glasgow, our Prime Minister also introduced Raman Panchamrita. So these 5 points, you can see that reach non-fossil fuel capacity of 500 gigawatt by 2030. Renewable energy, 50% energy requirements by renewable energy 2030. 1 billion carbon emissions reductions by 2030. Carbon intensity reductions below 45% to 30, and then net zero by 2070. Okay, I will tell you, most of you guys might have retired by the time, and I will be something around 90 plus years old. Most of the people won't be here. This is the first target. I don't know how easy to do that, because the countries like India is doing an exponential growth, more than we can accommodate or more than we can think about. It's dumping. There are a lot of research activities like global reproduction plan, CO2 separations and collection technology like absorption, adsorption membrane, etc. CO2 capture technology by bacteria, algae. And we work in the area of CO2 utilizations, chemicals and fuels, CO2 disposal technology, environmental friendly, productive technologies. There are a lot of R&D works are happening all over the world, and try to reduce the carbon emission. As a chemist, we can do that thermochemical pathway Photochemical pathway. Thermochemical means at high temperature and high pressure CO2 converting to useful chemical and fuel. Photochemical is a kind of, artificial, photosynthesis, we can say that. Electrochemical applied potential in the electrochemical condition, and biochemical by using some, enzymes or algae, etc. and all. If you look at thermochemical conditions, if you take a CO2 molecule and treat it with a hydrogen, it can be, either in the form of, one direct reactions methanol, or you can see that, here reverse water gas shift reaction on the right hand side, and it forms carbon monoxide. Or if you treat with the methane, so for example, if you go to biogas plant, majorly containing CO2 and methane, directly treat that one. Methane internally reform and that form hydrogen. That hydrogen will reduce carbon dioxide to form carbon monoxide, and then it will form methanol. Or if you use, some acid catalyst, that will be dehydration, and it will form dimethyl ether. Or it can be a methanol to gasoline or Fischer-Tropsch synthesis by, from CO2 hydrocarbon. This all process can be done by designing appropriate catalyst and proper chemical engineering. And in that one, engineering, you're talking about advanced CFT innovations technique. You can design the reactor and process engineering, everything. And if you go to, electrochemistry, apply the potential, particular potential, all this product can be formed. But the point is actually there will be a competition of hydrogen evolution reaction because it's actually happening in the water with alkaline or acidic condition. There is a competition. Hydrogen can be a major product than the CO2. So you have to tune the catalytic surface in such a way facilitating CO2 reduction. Efficiency and selectivity, they are the concerns. Stability is another concern in this case. If you go to photochemical, one of the major issues associated with that one is the selection of catalyst. You need a particular band gap, and you need a particular band gap with the band edge positions also at a particular positions that prefer for a compound that you are looking for. I'll give some examples. And the same problem here. Here also hydrogen is the one of the hydrogen evolution reaction is one of the competitive reaction. How to minimize that one? Or the other problem in photochemistry, all of you know that when electron hole recombinations, the excited electrons, this is a short-lived species, it may easily recombine with them in hole, and then you won't have enough electrons available for the CO2 reduction process. How to stabilize, how to attain the more electron at the surface. There are other techniques like you can see that carbon sequestration. That means actually CO2 can be pumped to the earth crust or in the sea level, under level, and then you can store maybe for 100 years or 200 years or more than that one and dig it as oil as we do now. Okay? Or you can store CO2. Here there are a lot of problems. When you want to pump it, you have to apply a lot of pressure to pump. That pressure is coming also in the form of energy input. That energy input is coming from somewhere energy production. That energy production is also associated with the CO2 emission. So when you try to solve this problem, you are creating the problem to solve that problem. Okay. When you go here, CO2 fixation, you can see that in the form of carbonate, cyclic carbonate, you take an epoxide and store CO2. Or you can make long chain species. But here the demand is actually you need high purity CO2. Or you can capture CO2 directly from air. So for example, Delhi weather, 600 ppm or 700 ppm is selectively 200 or 300 absorb. But the problem is actually nobody will invest the money. The reason is actually CO2, if you want to capture from coal plant, 1 ton CO2 capture cost is $40. If you want to capture CO2 from air, it is around $500. Who will invest the money? So it is practically quite difficult unless we will come to a scenario like a COVID. Everybody will come forward and do the job. So there are other technical terms. I will just go one by one. As per the Paris Agreement, the condition is actually the temperature should be 2 degrees below that whatever we are having. That means actually currently 450, you have to bring it down, or 420 or 30, that you have to bring it down to 350. And people talk about carbon credit. You can see that 1 ton of CO2 saved equal to 1 carbon credit. Say for example, if you stop your mobile for 1 year, you can save some carbon credit. Okay. Okay, so you just, walk from your home here without, using any, transportation. Yes, you are contributing. Or you plant, 46 trees, that is equivalent to 1 carbon credit. Or if you get just 1 CO2 saved by using the renewable energy, that is also 1 carbon credit. Or if you use, 1 ton of CO2 captured carbon credit, or 1 ton of carbon dioxide utilized to the formation of some different products, 1 carbon credit. Hopefully I have saved some carbon credit because I'm converting some chemicals at least in the laboratory scale. Okay, so it depends on the way you are handling. You can have the carbon credit. You won't be surprised, it's going to be introduced very soon, how much carbon credit you are going to have. And you will get a subsidized, benefit from the government also. So with this one, these are the activities we are doing in our lab. What we do basically, we capture CO2 and convert CO2 by photo, thermo and electro to the chemicals like methanol, methane, dimethyl ether, etc. I will show a few examples. And then we have a lab, water, hydrogen production or oxygen evolution. We, use this hydrogen that can be, already integrated with, this CO2 reduction. This hydrogen can be used in the fuel cell, as you see that one. If hydrogen is using, there is no byproduct only, other than water, only water. But, you can use the methanol that produced from this one, CO2 reduction can also be used as a fuel. In that case, carbon dioxide is also forming along with the water. And that carbon dioxide, again, you can capture back and then the cycle will continue. Okay? All this chemical process, what we do, we develop the materials as a potential catalyst to improve the efficiency and stability. So I will talk this part. During this course, we develop catalyst. That's our core expertise. You can control the particle size. You all know that when the particle size, the surface area will change. You can, control the shape and morphology, cube or sphere or whatever the shape you can make it. Lot of fundamental crystallographic, concept you can utilize. Proper support, whether it's a cube support or flat or porous support, etc. That also can be changed. The strong support, metal interactions also will facilitate. Or defects, you can tune the defects. You create the defect or feel the defects. That will change the electronic structure. That will change the thermodynamic parameters. Or single atom catalysts or heterostructures, alloying, dealloying, core shell, disordered 2D, confinement, etc. etc. All the chemical concepts, that we know under the sky can be efficiently explored or exploited to develop this material. I'll give few examples in this direction. Before that, again, fundamental chemistry. Why is so difficult? CO2. CO2 is a linear molecule. We all know that one. Because of the linear nature, it is very stable in nature, very difficult to activate it. Because of its linear nature, activation is difficult, and you can see that in the handbook. This table you can see, CO2 or CO molecule, all kind of, the product can be formed from the bottom, methanol, or this methane or formic acid, etc. And if you look at delta G parameters, and CO2, this chemical, there are two reactions can happen. One is actually, no change in oxidation state like carbonates. And another reaction, there is a change in the oxidation state. If you mean a change in the oxidation state like methane and methanol, you need a high energy input like temperature and pressure. Okay, so because of that one, it is not really favorable, thermodynamically limited one. And if you look at this one, carbon has sp hybridization. It's a linear non-polar molecule, triatomic non-polar molecule. Carbon has sp hybridization, and then oxygen has sp2 hybridization. And because of that one, carbon has a positive charge and oxygen has a negative charge, partial negative charge. Because of that one, carbon is electrophilic and oxygen is nucleophilic. So you have to have a metal or catalyst surface, either electron donor or electron deficient or electron rich or electron deficient metal surface. You have to create, to absorb the species efficiently at the surface. So when you do that, we can have the different, mode of, absorption can happen. Again, another fundamental part, molecular energy level diagrams. As you see that there are 16 valence electrons, and out of that one, this, 4 sigma HOMO is occupied, and 8 electrons, 2 pi LUMO. So that LUMO is actually, favoring whether you have to bend or straight. So this, facilitated by the proper adsorption of CO2 at the surface of the catalyst. This is a 1961 paper, molecular physics, and you can see that in the x-axis, CO2 molecule 180 degree or 225 degree this way, or this one is 135 degree. So if oxygen is adsorbed, it will actually form this way. If only carbon is adsorbing, it will form this way. When you do that one, in this y-axis, this axis, the actual bond length of 1.15 angstrom, that become actually elongated. Okay? So when bending happen, this is actually ending up in a elongation of bond. So the molecule is automatically activated with respect to the change that one. When you do this one, there are a lot of CO2 molecular adsorption happen. If you look at only one metal, C is actually adsorbed and it is forming a kind of a bend molecule adsorption. If you look at them in second one, you can see that this kind of mode. If you have 2 mu2 in eta 2, and you can see that M1, M2, and CO2 molecule, and then this is another shape. All these different kinds of the mode of engagement of CO2 molecule at the surface of multi-metal catalyst system is occurred. So basically, you are tuning the catalyst surface to design what mode of CO2 adsorption at the catalyst surface. And then, with all this one, we designed a lot of catalysts. What we have achieved, I will give some examples, what we have done. We produce ethylene, formaldehyde, ethanol, carbon monoxide, propanol, methanol, and series of compounds by different catalyst design by thermocatalytic, electrocatalytic, and photocatalytic methodology. And then I am bringing a mechanism, CO2 to C1 molecule. If you look at that, CO2 linear molecule as a first step. Can I get a better one, this one? So if you look at this one, CO2 bend, followed by hydrogenation, it is forming formic acid. And next step, it is a carbon monoxide, and then for formaldehyde, and then finally the adsorbed species either by dissociation of this red one and leave to methane molecule or methanol species. So it depends on what, whether intermediate species is strong or weak, actually, that will detect in which product is coming out. So the mechanism, it may lead into CO formation. If the CO is actually not strongly adsorbed, immediately that will emit and then it will form CO. If it is optimal adsorption followed by hydrogenation, it will form formaldehyde and further continues methane or methanol. I'll give few examples that we have discovered. Here, the first example, palladium and indium. Palladium is well-known catalyst for hydrogen evolution reaction. Everybody knows that one. But indium in the form of indium oxide is well known for CO2 to methanol. So when palladium and indium making a bond, it can form an intermetallic or alloy. Okay? So here we made an intermetallic, and the first case we protected with the indium oxide, and the second case without indium oxide. So the idea is actually indium oxide protection that protect palladium evolution, and without forming any palladium oxide surface. Okay? And in the case of palladium indium without indium protection, so it will form an palladium oxide surrounding. So you can see that in electrochemical condition, the Faraday efficiency on the y-axis, it is slowly increasing to around 75% over a period of 3,500 seconds, and you are getting. So the CO formation is changing with respect to the time, or with respect to the potential also, it's slowly increasing. So in operant condition, catalyst is tuned to have the production of CO. This is not really great results because already reported Faraday efficiency 100% for silver metal. So, if we go to the next one, syngas. Syngas is an industry, a synthetic gas. It is actually a mixture of carbon monoxide and hydrogen. The challenge is actually how we can produce synthesis gas in the ratio of 1:1. We have designed this catalyst. So for example, porous organic polymer with zinc. You can see that this one, zinc, it will produce only hydrogen. When it is only cobalt, it will produce only carbon monoxide. When you have an optimum condition of cobalt and zinc into the system, there will be charge transfer between the pi electron cloud of porous organic polymer to the metal species that is favoring for the formation of carbon monoxide and hydrogen and end up in 1:1 formation of syngas. Or if you take, non-metallic species, here again COF material, when it is in its linear one, there is no CO2 absorption. The moment it is actually bending, there is a charge transfer between these two species, what you call two rings, and that actually stabilizing, CO2 molecule at the surface, and then, CO2, that's the first step of CO2 absorption, further hydrogenation, carbon monoxide, as a various, as a one of the products in this case. Or here, if you take an intermetallic compound, nickel indium family, you can see that nickel, the left hand side, if you see that one, and indium here, when you make a compound with the nickel and indium, all these compounds, cubic or hexagonal at a different composition until triclinic system. And if you take a triclinic system, so you can see that the indium is actually in the cage of nickel. So we can say that one, it is a single atom catalyst. But here, we can say that it's a site isolation actually. So within the cage of, indium, so within the cage of the nickel, indium is actually protected. That is actually, acting as a kind of active catalyst towards the CO2, any other chemical reactions also you can think about. What we have done actually, we have taken mesoporous SPF15 as a support. And this SPF15 is very crucial to have a uniform distribution of active species inside the pore. And then you did a wet impregnation method. You can see that nickel and indium together forming compound inside, and then you can see that from nickel and indium together it is forming an intermetallic nickel 7 indium 3. We characterized by various techniques including microscopy, surface area measurement, porosity, etc. and all. So if you look at the catalysis, CO2 to methanol operate at high temperature and pressure. And if you look at this data, we apply pressure starting from 0 bar to 50 bar. And with increasing the pressure, the conversion and selectivity increasing, conversion increased to 16, and selectivity close to 80%. The state of art catalyst that reported conversion is 22% with a 70% selectivity. Okay, so because the CO2 to methanol is thermodynamically limited, we cannot go beyond that one. But the advantage here, this is operating at a 20 bar. Now the business side is coming to the picture. If you want to compress the gas from ambient condition to 20 bar, you need a single stage compressor. When you want to compress in a 40 bar, 2-stage compressor. When you go to beyond that one, triple stage compressor. Each will guard additional cost. So the cost of the compressor can be reduced by 1/3 compared to the state of art. Not only that one, the electricity that used can be also reduced by 30%, 40%. Economically, it will be very viable process if you are operating this one. So what is the chemistry here? We have taken the sample at a different pressure, whatever you operated, and did the XRD. You can see that at 5 bar on the top, it's matching with the triclinic, and slowly it is transformed to the different phase that is matching with the nickel 3 indium. Basically, triclinic system during the operanda condition that transform into metastable system. That catalyst is actually favorable for the conversion of CO2 to methanol. So we have done various in situ techniques to understand the mechanism. One such technique in situ IR. And if you look at this molecule nickel and indium, and these intermediates like a CH2O, CH2OO, or basically CH3O, CH3O could map it by in situ IR technique. On the other hand, if you take only methane, we are seeing only species CO majorly, but other species are not there. That is confirming this is actually going through this mechanism, and then the amount of indium also vary. Well, mechanism, comfortably in a different way. So we continued this work. So for example, instead of nickel 7 indium 3, changed to nickel 3 indium cubic, or nickel indium cubic, or nickel 2 indium in hexagonal, nickel 3 indium in hexagonal. So all this, composition we stayed, and then we did a study, how that in nickel to indium varies in the local, what you call, entropy, that local entropy, is changing, overall performance of CO2 to methanol in this case. So we can tune this catalyst in such a way, varying the chemical compositions in that one. If I take another example, copper. Copper is the champion catalyst already reported. At least 80% or 90% electrochemical materials are reported copper-based species. Gallium is another catalyst. Gallium in the form of gallium oxide, CO2 to methanol, reported. So we made the compound with the copper and gallium. These two compounds are reported in the literature, copper gallium 2 and copper 9 gallium 4. Copper gallium 2 is crystallized in the tetragonal symmetry, and you can see that copper layer, gallium layer, copper layer, gallium layer, and it's like that one. It's a kind of two-dimensional structure. On the other hand, you can see that copper 9 gallium 4, this is a three-dimensional structure, cubic system. The idea is actually when you have a layered structure, in the electrochemical condition, copper or gallium may etch it out, dissolute, and it will form an oxide layer at the surface of that one. If gallium is forming an gallium oxide, it may favor for the formation of CO2 to methanol. So with the induction, we got the data in electrochemical condition, and you can see that at potential here, around 80% of methanol is formed, Faraday efficiency. And if you look at this in the case of copper 9 gallium 4, it's around 40%. Okay, so what is the chemistry behind that one? So both are forming methanol, but in the two-dimensional case, it is forming 80%. This is one of the highest production of methanol by electrochemical pathway. Anyway, we have done in situ study, in situ IR, and you can see the two peaks. You can see that. OCO species, OCHOP species, or this bridge species also. And as per the two literature, you can see that it can go through the path 1 or path 2. And you can see that this species corresponding to this one or this one. So basically, observation of these two species is confirming this is going through path 2. You could not identify this, no? Yeah. So then, if you go further here, and I just go here, that is better. If you go here, in situ, X-ray absorption spectroscopy, if you take a copper edge, okay, copper gallium 2 and copper 9 gallium 4, there is no difference. But when you go to the gallium foil, X-ray absorption spectroscopy, gallium edge, and this one, gallium foil, copper gallium 2, copper 9 gallium 4. In the case of copper 9 gallium 4, there is no difference, but copper gallium 2, there is a peak corresponding to gallium oxide. Okay, so that is a major driving force. And then when you did in situ XPS, pseudo in situ XPS, at lower potential there is a gallium 3 plus, and here at higher potential there is no gallium 3 plus. In the case of an oxygen 2s species also, you can see that it is eliminating with respect to higher temperature. And then we take the ratio of gallium 3 plus to gallium 0, and you can see that lower potential for copper gallium 2 close to 90% of gallium oxide. So that's the reason actually the gallium oxide in copper gallium 2 is having higher amount of gallium oxide. That gallium oxide is actually favoring for the CO2 reduction at that lower potential. When you go to the higher potential, this is becoming gallium metal. Very good, thank you. So then, this paper took actually 1.5 years to during the review process. So the reviewer was not happy, and we had to do some in situ experiments at synchrotron, and you can see that with respect to the potential, the gallium oxide peak is reducing. That means gallium metal, and then gallium metal is increasing with respect to the potential. It's confirming that at higher potential gallium metal is more, at lower potential gallium oxide is more. And it's also copper oxide is also more in the higher potential. That copper oxide is actually not favorable for the CO2 to methanol formation. Then finally, again referee came back to us. You have to do flow cell. That means actually you have to increase the current density. So if you want to take any material for electrochemistry, the current density should be more than 1 ampere per square centimeter. But here it is not really that great. But anyway, we have set one flow cell for electrochemical set conditions, and then we set all these parameters, optimize all these parameters. And I just want to show the data here. It increased by 20 times compared to the batch process, and the stability over a period of 24 hours without changing any periodic efficiency or current density. And we compare all the data, whatever reported in the literature, you can see that at lower potential, it is 80% periodic efficiency towards methanol. So, still it is holding the record. This is the highest ever periodic efficiency for methanol by electrochemical method. I'll skip that one. So now, that's the C1 molecule. If we jump into C2, so you can see that there are a lot of, the mechanistic pathway. If I take two of them, it can go through ethylene path or it can go through, ethanol pathway. So you can see that the step 1, 2, 3, 4, I'm up to here ethylene. If you just divert this mechanism this fashion, acetic acid, if you go this way, glyoxal, glycoaldehyde, ethylene glycol, acetaldehyde, ethanol. Basically, all these molecules can be formed from CO2. It ends up in a huge problem in the selectivity. So, if you want to have 100% ethylene formation, it's a difficult task. Along with the C2, you will also end up in C1 molecules, like a CO, methane, formic acid, etc. So that's one of the challenges. This is basically associated with the CC coupling in this one. Anyway, I have some examples what we have done. Here, this is photochemical method. The red phosphorus already reported for CO2 to formic acid. For example, the band edge position here is actually well matched for the formic acid. What happened actually, the efficiency is very low because of the electron hole recombination. We have introduced some bismuth molybdenate in the system. Whatever excited electrons tap into the band edge of this one, and minus 0.33 is corresponding to ethanol. Well suit that one. And even you can tune that 0.33 by tuning the oxygen deficiency. You want to go to 0.34 or 0.32, you can tune that one. And we made different composite, and we got around 55 micromole per hour per gram of ethanol by photocatalytic pathway. And what we have done actually is just a simple probe sonications method. We have a layer of red phosphorus and bismuth molybdenate nanoparticle, and with a different sonication time, the layers separated around 20 hours. Separations you got around 55 micromole per hour per gram. And my students also did this test under the sun over a period of 8 months. Summer season, winter season, morning, evening, etc. And then you can see that somewhere in the early June period, summer season, and you can see that close to 35, it is around 70% compared to the artificial light that we used in the lab. It is not really great, because it's in the early stage, like the solar cells started in the 70s and 80s, efficiency is very poor. Those were two material, but when you go to single compound, you can see that bismuth sulfide, this is already reported for CO2 reduction. The structure is a ladder structure, only one bismuth 3+, and we introduced chlorine into that one, and this compound changed to bismuth 19, SN27 chlorine 3. You can see that chlorine is nicely packed in the pocket and making a star shape. And this ladder is discontinued here. And then you can see that the bismuth is split into 3 crystallographic positions of bismuth. One bismuth is sitting at the middle of the star, bismuth 2+. Another bismuth is sitting here, bismuth 3+, delta plus, and this 3+ delta minus. So split into 3 positions. So because of the charge polarization, the intermediate that forms stabilizing at the surface, the intermediates can be CO, CH4, CHO, COH, etc. That stabilize, and with this one design, this one changed from this yield of actually no ethanol formations in this case. It produces ethanol because the intermediate stabilizing, and these two bismuth 3+ delta plus 3+ delta minus very close range. Because of the stabilization, there is a reasonable distance for the CC coupling happening and further hydrogenation, and it is forming ethanol. And ethylene. I'll skip this one, I'll go one other example. Here, if you take a Wurtzite structure, you all know that one zinc sulfide, Wurtzite structure, and the left hand side of zinc is copper +1. Right side is copper, gallium +3. So we substituted zinc with one equivalent, half equivalent of copper and half equivalent of gallium, it is a 1:1 at the same position of zinc. So by this one, created a lattice strain and charge polarization. When we did this under photochemical condition, this copper slowly come out, it will form copper oxide, CuO. That copper oxide is a +2, and copper gallium S2 is +1. At the interface of a copper gallium S2 and then copper oxide, this charge polarization of copper +1 and +2, that is actually favoring for the CC coupling efficiently in this case, and we beat our own record. Earlier paper it was something around 120, this is a 200 micromole per gram of the catalyst we produced. I'll skip this one also. If I go to acetic acid, we have done, we have selected AgBs2. There is a disordered species, that means silver and bismuth are occupying at the same atomic position. When you substituted with the sulfur with the selenium, silver and bismuth ordered, that means silver has its own crystallographic position, bismuth has its own crystallographic position. And copper is the variant of AgBsE2. That's a copper variant. So the idea is actually silver is well-known catalyst. It will form silver oxide in the electrochemical condition. By doing this one, AgBsE2 is actually showing a good in a conversion of CO2 to acetic acid. So what is the chemistry here? If you take this disordered species, the metal shortest distance is 4.89. That is not favorable for the CC coupling that easily. The moment it is an ordered compound, the distance between this metal center 3.08, that is very close. So because of that one, more CC coupling can be favored. In the case of copper one, it is slightly bigger, so automatically the amount, the yield of acetic acid is lower. Okay, so how much time I have? Okay, so if we go to propanol, you can see that I'm entering into the C3 world now. So here, one example we publish, rather it's about to be accepted. You can see that palladium and copper, I did not mention here, palladium and copper based compounds are reported at least 50 times in the literature for hydrogen production, fuel cell, even CO2 reduction, various concepts. Here what we have done, we made the compound in the form of sphere, in the form of cube, and if you know the crystallography, in the form of sphere, the crystallographic plane exposed is 111. In the form of cube, crystallographic plane is actually 100. The packing density of 100 is different from 111. Automatically, when the packing density is different, the bond distance also will be different. That will change actually, strain also introduce more active in nature. So this idea exploited, and we characterized, and we found that both compounds are forming propanol. You can see that ethanol formation is also happening, that is C2. Here propanol formation, that yield, in the case of cube, it is much more. In the case of this cube, periodic efficiency is also much more. So the crystallographic, the morphology also tuning the selectivity to a desired product that you are looking for. So then, this is another compound. Again, I am going back to 112 species, Ag indium S2. It's already reported in two crystal system, tetracline and orthorhombic. And there are series of compounds reported in this family, as you see that one. This is a structure here. And you can see that orthorhombic, there are 2 sulfur atoms, and in the tetragonal species, only 1 sulfur. And we have computed the electronic structure of both species, and you can see that at the bottom, the energy levels are kind of a discrete layer, it's actually well separated. It is easy to shuttle the electrons from one level to another level to another level. On the other hand, if you take a tetragonal system, this is actually single one, electron shuttling is not easy. So automatically the charge distribution is also different. Charge will be well separated in the case of a tetragonal, but orthorhombic it is not the case. So we have calculated the Hirschfeld's charge analysis, And you can see that orthonomic system of Ag, indium, Se2, all you can see that. But even here you can see that charge distribution is very small range. But when you go to the tetragonal copper indium system, it's selene system, charge is more. So when charge distribution is more, it will end up in actually C3 products. You will have, in the charge polarization much more, in the case of, more charge distribution. And it end up in, C3. On the other hand, in the case of tetragonal Ag, indium S2, that's somewhere here. And in the case of copper indium Se2, copper indium Se2, that is also here. And less charge separation, that end up in only C1 and C2 product. We also varied the silver with the copper partial substitution, or indium with gallium partial substitution, or sulfur with the selenium partial substitution to vary the charge distribution. By doing minute changes at the atomic level, we can vary the product selectivity. So last example in the series, C6, iron oxide. Iron oxide is well known for, olefin or paraffins formation. So what happens actually when you take iron oxide, treat it with the carbon dioxide at high temperature and high pressure, it will form iron carbide, Fe5, C2 or Fe3, C1. So this is actually well known, and you can see that kind of a tandem catalyst, CO2 will adsorb followed by CO and then into hydrocarbons. It can be through this Fischer-Tropsch synthesis or methanol to olefins via methanol formation, etc. So what we have done, we introduced indium oxide. Indium is actually similar size as iron. Indium is +3. Iron is there also +3. So we substituted and actually vary this, the lattice strain. I can see that 2%, 5%, 10% indium substituted, iron oxide, support on alumina, and activated. You can see that's a compound form. Higher indium oxide, it will separate as indium oxide formation, but lower one, indium is well actually substituted the iron position. And then when you do this synthesis, CO2 reduction, you can see that this molecule is forming iron carbide along with the indium substituted Fe3O4. So this indium substituted Fe3O4 creating a strain within the system that's changing the mechanism towards the higher alcohols. And then you can see that 1% higher alcohol, 2% is much higher. When you go to 3.5% of indium, it is reducing because it is forming more, lower olefins or alkane species. And when you this one, fraction of that one C4 species, that's nothing but butane, and even pentane, heptane, octane, isobutene, etc. All this kind of hydrocarbons, around 40% of, yield, 40% of selectivity for the hydrocarbon. What happened actually, when it is in only Fe2O3, CO2 adsorption is this much, this is increasing with respect to indium substitution. Further promotion with the potassium is increasing CO2. So more CO2 is actually available at the surface. That is favoring for the better performance towards the CO2 reduction and further. If you just summarize this way, if it's only a Fe2O3, it will end up in paraffins. The moment you introduce indium oxide and it forms, along with Fe5C2, these together act as a tandem catalyst and it will form higher alcohol and olefins. Okay, out of this one I take, one molecule. All this one produce series of compounds. Nowadays, we are getting more than C10. Some of the early results we have C18, C16, etc. and we are producing. And if you look at this one, methanol is actually, considered as a future fuel. It has a low risk of flammability. It can be used in a fuel cell. It can improve the performance when blended with the gasoline. M15 is well known. Or M100, there are 20,000 taxi cars introduced in Beijing. M15 introduced by Niti Aayog as a part of the government policy. A20, that is the 5% of methanol, 5% of ethanol, 15% of methanol, and the remaining gasoline that introduced by Italy. M15 Israel, etc. So different countries, different target. Eco-friendly, can be used in multiple applications, renewable sources, sustainable, versatile alternative energy for the future, more stable than hydrogen. So now people are thinking about the marine fuel, methanol as a marine fuel. You all know that when we have Vizhinjam seaport, it's already, inaugurated. So the idea is actually the big gigantic ships, they will have a stop here in Vizhinjam seaport. And if you see one ship traveling from Tokyo to Boston through this road, 5,000 tons of diesel required. Okay, and just imagine, I put it a C8, H18, 5,000 of, that diesel burn, how much, CO2 produce? Okay, so the idea is, can we replace, this diesel with the methanol? This is one of the target. And this is $1 million business. And there are around 280 to 300 ships in a year that stops in this seaport. Okay, this is one example, and this will reduce the pollution. This will also, create the efficiency and then economically viable. Why methanol is so important? So if you look at that, methanol can keep the existing infrastructure. Whatever the pipeline we have, the gas lines and everything, can keep it. You don't have to change. Some modifications required. Gas stations, whatever the pumps, you are seeing that can be changed with, some additional investment. Methanol is safer than, gasoline, high octane ignition temperature. Methanol can blend with the water infinity and can be decomposed by bacteria. Say, for example, oil spillage of marine ocean. This is one of the problems. Okay, so methanol, if that's the case, it is easy to clean it. Internal combustion engine modified because methanol has a problem that one, it has a dipole moment, corrosive nature. It may, damage, the component that involved in that one. So it has to be protected or, engine should be modified. High octane number, you all know that one efficiency associated with the octane number 106 compared to 90 and 100 diesel and petrol. And no, no SOx, etc. that will have damaged the catalyst and performance, the stability will be problem. If you compare them in energy content per volume, you can take, best example, diesel and gasoline, or the future course, in a hydrogen. 1 atmospheric pressure hydrogen, you see that almost, energy zero, close to zero. If you want to have that one, you have to pressurize 200 atmosphere or 350 or 700, or you make it as a liquid one. When you want to make, you have to put a large amount of energy to pressurize that one. That energy is also come with, pollution. That energy also come with, cost involvement. And when, you look at the pollution and the cost involvement, some are medium optimized conditions. So it's nothing but, here, you can see that ethanol or methanol. But ethanol, the challenge is actually compared to methanol, because of the strong CC bond, this oxidation is quite difficult compared to methanol. With all this, idea, so methanol can be considered as one of the best future fuel. And when the oil crisis happened, way back in 1970s, you all know that one, why this oil crisis happened. Because of the Cold War, and there was, in between the countries, there was limited, transportations, and at that time, methanol economy was introduced. It can be considered as a future alternative fuel if such scenario continue. And there is another science paper, you can see that this man filling methanol in Chicago in 1991. And this could not continue there because ethanol was cheaper. Ethanol can be produced from, fermentation process quite easily. Or you can use, corn or whatever, that also easily, burn it and then you can produce ethanol easily. Because of the production cost is much better in the case of ethanol. And then, these two gentlemen, George Oleg, he got Nobel Prize in 1991 for his contribution in carbonate chemistry. And he is a Bangalorean. He joined as a PhD with him, 70s. And he never left his boss. His boss passed away, still he continued the same place. Still he is a professor there. But they commissioned one plant. They started in 2007. George Ola CO2 methanol plant in Iceland. With the capacity, you can see that 4,000 tons of methanol per year. That means, in approximately 1 ton in a day, divided by 365, close to that one. And then, they use, the electricity. We are talking about the electricity. The electricity they use is geothermal electricity. So they have a lot of springs. The hot springs are available. They use that electricity. The cost of the electricity almost negligible, close to zero. but we don't have the luxury of that one. So if you want to take this plant to India, it is impossible. Because 1 unit of electricity costs 7 rupees, 8 rupees, that vary. Okay? When we talk about a solar pan, we need a large area to have the solar pan. Wind is, geographically restricted. So all these problems, we cannot have this one. The catalyst developed by Johnson Matthey, I was talking about 22% conversion, selectivity 70%. There is a plant initiated in Germany, but that plant didn't ever completed. There is a plant, in India also developed in 2019. After 2 months, it shut down because the cost was very high. Methanol price in the market is 40 rupees. The production cost in that plant, it was 89 rupees. Who will run the plant? This is a 300 metric ton plant. Anyway, they took, in 10 years. Still they are, improving the efficiency. And we have developed, a lot of catalysts over a period of 6-7 years. If you start this term, space-time yield, that's nothing but gram of methanol per gram of catalyst in an hour. And you see this number, 0.3, 0.6 goes on, and then we reach somewhere here, 4.3. Some of the debates, you can introduce the calculation may not be absolutely correct because the calculation based on the active catalyst you are using. Say, for example, if you take nickel at the surface of cerium dioxide, you just take that nickel as active species, but cerium oxide also contributing that one. So several mistakes in the literature, you can see that one, the way you want to address, they can calculate. And you can see that this is a catalyst we scaled up, 0.6. If you don't know, we were the part of in a global competition, $20 million gold energy cost X prize competition. We were the only Asian team in the final round of the competition. And we scale up the catalyst and demonstrate the plant in India and then demonstrated to various national and international agencies and then validated. So I just pause that. I will come back. How much time I have if you want to jump into this one? Still 15 minutes. So we also work in the area of water splitting. We produce hydrogen. I will give one example. So if you look at the hydrogen, hydrogen is the hot topic at this moment. As I mentioned, everybody say hydrogen, hydrogen, hydrogen. But the problem is actually, hydrogen, how to store and how to produce the quantity you are looking for. 1 kilogram of green hydrogen costs at this moment 300 rupees. It is impossible to use that hydrogen for any economical process. 1 gram of grey hydrogen cost is around 120 and 150 rupees. Even then, that is not possible. When, if it is a grey hydrogen, the amount of CO2 that produced, gigantic. So it is a challenging task, but the cost you can see that 12 euro and 10 euro per kilogram, it should be, by 2050, it should be 4 or 3 or 2, whatever the best you can think about. And the demand is actually, you can see that by 2070, but we are talking about net zero. If you want to have a net zero, you have to have, this much million metric ton of hydrogen we have to produce. Okay? The problem, if you want to produce hydrogen, green hydrogen, you need water. And water should be in pure form. If you are using, water purification unit, only 30% of water will be purified water, the rest you are waste. Okay? And Indian population contribution 17% in the global population. But our groundwater only 4% global percentage. So 4% and 17%, and then you are taking that 4% further to produce hydrogen. Not only that, when you purified, the impure water, that is actually damaging your soil also. There was a study in Bangalore, the metal content in the fruits is actually really high. Really high. And that fruit content, metal content is actually how much is going to damage your organ. All this, brain and everything is going to be damaged. Unknowingly, you are eating something, unknowingly, you are damaging your health system. So, it is not really easy, but we have some interesting experience. We develop again material, this compound, platinum 3 germanium. It's already reported. Platinum is a champion catalyst for the hydrogen evolution, but platinum is expensive. But at the same time, platinum can be improved. The efficiency can be improved by introduction of a second metal into the system. You can see that platinum 3 germanium is a tetragonal species. There are different crystallography planes. We computed different crystallography planes and which one is favoring for the best catalytic activity. Theoretically, And we synthesize two phases, 110 and 202. I'll come to the chemistry. And we characterize that one. So you can see that germanium atoms, platinum atoms in the germanium metal and platinum metal, when it is a disordered alloy, you can see the random distribution of platinum and germanium. When it's an ordered one, you can see that ordered way, one germanium atom surrounded by 8, so you can see that platinum in a two-dimensional manner. And we have tested this catalyst. We introduced the term fabulous 5. This means, 5 fundamental electrochemical properties, improved with, respect to platinum and carbon. You can see that, for example, current density in the case of platinum and carbon, something close to, or less than 1 ampere per square centimeter is improved to 2 ampere per square centimeter. You can see that durability increased by, almost 3 times of that one. So all these properties actually change, dramatically, to the whatever the best, you can think about it. So the chemistry, if you take, 110 plane, that containing only germanium. In the case of 202 plane, it is containing, both germanium and platinum in alternative arrangement. So we did in situ exapts. You can see that platinum edge, the absorption energy shifting to the lower side, lower energy, and for this germanium is shifting to the higher energy. That means actually there is a charge transfer between platinum and germanium at that particular plane. So platinum 3 germanium 202 plane is actually more active compared to 110 because of the charge transfer between platinum and germanium. This also associated with the binding of the hydrogen species at the surface of germanium or platinum. And if in the case of this only platinum, it will be weaker in nature, reaction will be less, and relatively stable in the case of, if it is in the case of ordered arrangement of platinum 3 germanium. So we have, this we tested in the smaller scale in our lab. We also integrate with the fuel cell, this electrolyzer that we constructed. And this is the plant we have within Bangalore. It is shifted to different place. Earlier, the plan was integrating with our CO2 reduction with a capacity of 20 nm cube per hour. We are in discussion with someone to scale up the catalyst to test in the larger capacity. Anyway, we have done this, so our potential studies also in 0.5 molar H2S over acidic media. And the platinum 3 germanium 202 is showing a quick, what you call the best, our potential compared to all the platinum species reporter for hydrogen evolution, at least in the laboratory scale. We also, did in alkaline condition. You can see that for 72 hours, around 500 milliampere per square centimeter. This is one of the highest one reported in terms of, current density in the platinum series. Okay, so we have series of work. What we have done, we have CO2 capture, CO2 reduction, and hydrogen generation. At the point, how to integrate all together. We started this journey 2016, 17, 18, that period, and then in our campus, new campus, this is collaborate with the partner, CO2 capture. This is CO2 reduction and a fuel cell. This is recycling. This is distillation unit. This is a hydrogen generation unit. And then over a period of time, so we did accept the CO2 capture. At that time, we used the CO2 from the cylinder. And hydrogen also we used a cylinder actually, because hydrogen generation unit did not install. And then, finally, it's a kind of, how this methanol can be produced. That's what we are working in a different place. So this is a plant, this building 1 to 12, when you can see that 12 when student is collecting methanol. This is a capacity of 300 kilogram of CO2 per day. See, 300 kilogram of CO2 per day capacity. We can do it in the campus. And then with this one, with the recycling, we can produce close to 150 to 170 liter of methanol per day. So we have also calculated, in fact, a third party calculated the methanol cost by utilizing the utilities that we had in our hand. 20 to 24 rupees per liter. It is a smaller scale. Compared to the market price, 35 to 45 market price. Keep in that this is a production cost. Market price associated with the additional cost involved in that one when it comes to the market. And at the moment, international market, it's varying per liter. It is in the range of 21 to 24 production cost. We are in that line. And you can see that Asian Pacific region, this is one of the most fastest growing region, and then China definitely. is the leading market, I mean, for the methanol. And you can see that 36.3 billion projected, methanol, this, business is happening here in 2026. So currently we are working on this same technology. We are building a plant in Telangana. In fact, I was there last week. And we are planning to commission the plant by end of this year, probably December 25th. And this is a power plant, 650 megawatt power plant by Telangana government. And this is funded by CMPD and CAL. And this, we tap CO2 from here. There is a small unit, desulfurization unit. We remove the sulfur excess where. And along, around 3 kilometer distance from here, somewhere here, we have a plant, it's building. And we have all these units, there. And you can see that various pictures recently collected. All the pipelines started, the building erections, and then, this one, and they're expected to be this building by end of December. If not, maybe, here or there, some difference will be there. So, this is a process flow diagram we use. So, my MTech course actually helped me a little bit to understand the chemical engineering. There was a little bit portion, engineering aspect. At that time, I learned this one. So, here you can see that from here, the unit 1, desulfurization unit, hydrogen generation on this, spot, by 60 nm cube per hour capacity hydrogen per day, per hour. And then unit 2, CO2 capture by amine-based technology, whatever the desulfurized, removed the sulfur, the rest capturing. And then, this is compressed to 50 bar, here also 50 bar, mixed together with the preheater and the reactor that we have the catalyst. And this methanol will produce along with the water and then distilled and then purified. And this will, recycle back. The thermodynamic conversion is only 30%. The remaining 70% recycle back. And then, making, close to 80% conversion. So these are the various part of this building. And then you can see that one or other units are building up nicely. And the desulfurization unit. And we are making methanol. Okay, I will take 4 or 5 minutes just to conclude. Finally, we can use it in various applications. One example we use in our lab itself, fuel cell. Or methanol can be used for the formation of dimethyl ether. We use, LPG gas in our home. If you blend that LPG cylinder with the dimethyl ether, the cost now 815 something around. It can be reduced another 100, around 700. A house that use 3 months, this cylinder, the efficiency can be improved for 4 or 5. By reducing 100, increasing the efficiency, it is a beneficial. So the government of India through Niti Aayog already did that one. But here methanol can be used here, anode and cathode. Basically methanol anode side, methanol oxidation reaction, and the cathode, oxygen reduction reaction happening. I will skip all this one. So, well, so we can use it, integrate that one, whatever the methanol production, or methanol can be used for the production of olefins. For example, we can produce ethylene. Ethylene is a good, for the polyethylene. Or you can, methanol can be used for dimethyl ether, as I mentioned, or you can use it for higher alcohol, or you can use it for the sustainable aviation fuel also. So these are the projects we have in our hand. We are working with the Tata Steel for CO2 to gasoline, CO2 to methanol, syngas, and then to gasoline. We are working with the sugar industry. Sugar industry, the advantage is actually this is a fermentation process. There is no need of purifying CO2 further. Each sugar industry around 20 to 50 ton of CO2 every day producing by this process. If you take only, UP, there are around 80 sugar plants are there. 80 multiplied by 30 average. 10 of that one, 240 ton of CO2 producing from only sugar plant in only one state. Maharashtra second best. So this all, CO2, we can efficiently utilize. The cost will be much lesser. So we are working with one Pune firm, Kunchir. So this is about to be started. We already work with the Bharat Petroleum, BPCL, CO2 dimethyl ether. We are working with HB, CO2 ethylene formation. And finally, we have a center of excellence first in the country, funded by DST, aiming for all the facilities that we can think about CCU, not S. We are not doing sequestration. Here, actually, we develop the fundamental science, fundamental engineering, but the focus is science. Engineering is collaboration, and we don't want to claim that engineering is there, but the technology, development, scaling up the catalyst, scaling up the process, we have all the kind of units available. You can think about anything related to CCU, we have in hand. Whether you want to measure, in situ studies like in situ IR, in situ Raman, in situ mass, in situ XRD, in situ XOPS we do, in situ EPR we do, pseudo in situ XPS we do. So all kind of in situ techniques we do extensively in that. Or we can scale up the catalyst for thermocatalytic half a cc catalyst loading to 6000 cc catalysis loading. Now that is, more than something around 15,000 cc catalyst you can test in the bigger reactor. So facilities we have, and then we reached, last year, we took, 1 year, 5 years to publish first paper. We started in 2015, 16, we published first paper in 2021, the original article. But next 3 years we published, around 30 plus articles. So it took, long period, to have the first article before setting up, and then you can see that the journey started. Thermo, electro and photo, if you take it the thermo, you can read, this all publications. I already posted in this Twitter. And then, this is a electro, and this is a photo. Another maybe 10 under review or revisions is currently going on. We can think about a lot of dream projects. Currently, we are working CO2, CO, DRM process. As I mentioned, CH4 instead of hydrogen. Hydrogen production is a concern. So we can use methane. Methane is other greenhouse gas. Internal reforming and can be converted to. So some of the initial results are very potential. 90% CO2 conversion, 99% methane conversion we got. CO2 to carbon nanotubes. We have some results. And we can already reported certain things. But this can be done. CO2 diamond. One Nature paper recently came. We also got some results, but we are still confused whether it's a diamond or not. But 1200 degree, yeah. So if this paper reported diamond, it is another dream project you can think about. Just a couple of days back, CO2 food, what you call glucose. Or the form of the glucose. So that is reported in Nature again. So that can be also kind of artificial synthesis. You can do it. So CO2, gasolines, you can see that the mechanism first CO followed by hydrocarbon and followed by C5 to C11 molecules. We have something interesting result. Or the sustainable aviation fuel. Continue that one to C12 to C18. We can consider C6 to C18 also sustainable aviation fuel. So we are currently in discussion with one industry sector to how it's almost there. So we may start. This is one of the hot, I would say, holy grail of this technology so far. Recently, I was traveling one of the cities, one city to another city, and then the pilot was announcing while landing, if somebody in the aeroplane working in the area of a sustainable aviation fuel, please contact Eurowings. We are happy to collaborate with you. So that is the interest actually. I felt so good, but we had to contact. With this, I would like to acknowledge all the funding agency. As Dr. Manoj mentions, and we got a lot of funding. Many people are coming forward. Many of them know not taking, to be honest. Many people, because it's a hot topic, many people want to contribute to the net zero by doing this kind of research, even fundamental research. I'm not talking about the translation research. And all the collaborations, various people involved in that one. And the best, my students, over a period of time, I was lucky to have, excellent student, vibrant students over a period of time. So many of them are, she's here, she's sitting here. And many students actually contributed in the development of the catalyst and then various technology development. And I just want to give this summary with the first sentence I told that one. This is a kind of inspiration talk. If you really want to do something, this is your passion. You can do it. I never thought about I will complete even BSc, to be honest. Okay. So with this one, I conclude my lecture. Thank you very much. If you have any questions, I'm happy to answer that.
It was a really wonderful presentation, and for me, like a kid, I was watching this movie of building, shopping the periodic table, putting the building blocks at the right place with the right thought and design, and achieving something really great. And we were never thought about this kind of research when we started doing this. And I think India didn't have these things in one place. And this involves a lot of courage, a lot of planning. And thank you, Dr. Sebastian, for putting things in place and showing the young minds how to carry out things. That was really a big applause to him.
Thank you.
I believe that this is a highly entropy demanding work.
Yes.
To put things in place and having, especially the higher alkanes series that you try to generate. Which one, in your opinion, became efficient? Ethanol or higher alkanes?
Well, so ethanol, it's quite challenging task from CO2 because of CC coupling is an issue. Other route for ethanol formation is relatively easier compared to methanol. But methanol, it has its own challenges, thermodynamic limit, and we cannot do that one. But CO2 to methane is relatively thermodynamically feasible process, but methane is another greenhouse gas, so nobody want to do that one. Each one has its own problem. So we are trying hard for methanol because methanol is considered as the scientifically challenging product. But if I spend this field 10 years, another 10 years, probably at the age of 55, I want to crack sustainable aviation fuel. That's why my dream project. And then if it not happen, I just leave the place and then leave. That's all.
Thank you.
So that is a challenging task. I initially put 5 years. It is difficult. It is difficult. When we started 2016, to be honest, I did not have a single GC also. I did not have lab, I did not have GC, I did not have reactor. From the scratch, zero, nothing was there. Even I knew that on what is CO2 molecule, CO2 is a linear molecule with a point group D infinity H. That's all.
We remember he came to our department and gave, probably in 2016,
Yes, something like that.
and talked about your plans on building this.
Yeah.
It was
So it is long way to go.
Yeah. It's time for you to ask and interact.
Questions. Nobody answers question.
You have talked in detail that designing the catalysts itself, I think there was a lot of theoretical work behind.
So many are there. So many works are there.
Sir, good afternoon, sir. My Chinchilla. You said that the cat used water. The process will be a code.
I did not get the question. Okay. Very good question. Okay, so everybody talk about, if you read the article also, people talk about when non-platinum based catalyst develop, they say that when platinum is expensive to replace platinum, we develop this non-platinum compounds that can be potential alternatives and all. But industrially, the regeneration of metal platinum is the best. More than 99% of whatever use the platinum, you can regenerate it. But if you go with another non-platinum metals, say for example copper or iron and everything, you cannot regenerate it. In that sense, once you have the investment on the platinum, it is stable. On the other hand, platinum has the work function chemically as, I mean, one of the best in that any metal you can think about it. Now, earlier platinum was more expensive than palladium, but palladium is double the cost of the platinum. Palladium is the second best metal compared to the platinum. So palladium cannot be used. Even when I started my fuel cell or electrolyzer research at that time, platinum was half the price, so double the price of palladium. Now platinum is the half the price of the palladium, because the large abundance of platinum discovered in South Africa, that reduced the cost dramatically. So that it will vary with the availability, it also vary with the industrial regeneration process of the metal. Say for example, after 20 years your electrolyzer, you have to actually, what do you call, regenerate or just modify or new what you call electrolyzer. At that time the whole platinum you can recover. There is no issue with that one. But if any other metal, it's not that easy and straightforward.
Hello sir, myself Amy. So I have a doubt that in that
Mic has problem. You can talk.
Yeah, you are loud enough.
Hmm. No, I mean we can use it. We have tested both alkaline and acidic condition, even neutral condition also. The performance in acidic condition much better than the alkaline condition. Alkaline conditions, I mean, the problem is actually the stability, one of the concern because of the media that we are operating. Acidic condition, I mean, so for the CR is much favorable. So this catalyst is stable for, we tested there 500, even we tested beyond that one, 500 cycles we have tested and it was stable. But alkaline is also stable. We tested for 72 hours, but the performance is not as good as acidic conditions. But the platinum may not be required for the alkaline condition. Better to use nickel or the less, I mean, what you call economical, I mean, economical, less cost, lower cost, I mean, nickel can be used. Not required. But again, pure water means, I mean, some contaminants will be there in the impure water. That contaminants, as long as if you don't know how that affects the catalyst, you don't know. If the contaminant sulfur, nitrogen, or there are other chlorine, etc. and all, it will poison the catalyst. It will strongly adsorbed at the surface of the catalyst and that will damage the catalyst performance. So that is one of the reason, I mean, pure water. Here pure water in the sense water plus the alkaline media that you are changing the pH one. But the contaminants means other species like sulfur, chlorine, etc. That will damage the catalyst surface. That's one of the technical challenges. You have to purify water at any cost. Okay.
Many of your work was concerned with this metal oxides and such things. Why don't we go for a ligand encapsulated metal center for such kind of applications?
Yeah, it is reported. So the problem is actually we cannot have the compound, if you are talking about CO2 reduction, most of the ligand metal that at the center, that will form only C1 molecule. So most of the products are basically carbon monoxide. If you look at the literature also, for that one it is good. But if you want to have something different, for example methanol, you need to have a metal center that should provide hydrogen dissociation followed by spillover of the hydrogen to the metal active species. And that if you don't have, it will form only CO molecule. So for that purpose, I mean, we change it. But nothing wrong with this one also if you are looking for CO.
Then in one of the slides, I found some zinc encapsulated some organic.
Porous organic polymer.
With kind of an imine kind of.
Correct.
With some hydrogen evolving.
Ah.
My concern is, whether is there any possibility that during the course of the reaction, when suitable potential is given, that imine bond get reduced due to the presence of hydrogen?
In the small quantity, we did not see that one. Possibilities are there if you accumulate in the large capacity, probably it's there, but we do not see that one. Okay. Yes. Yeah. Yes.
Thank you for the very informative session. And please tell me the strategy that you have followed for the LC analysis.
Oh, yeah. Okay. So LC analysis, basically we start from the scratch. If you want to, know the software, we use SimaPro. So this is a standard one we used academic license. We have a inbuilt data, depends on which country the data is available. Say for example, if you are calculating life cycle analysis for India, the data available in India, for example, the electricity source coming from coal, the data that inbuilt into that program. Okay. So for example, catalyst synthesis, use this much chemical, this much temperature, this much water, etc. That you automatically build there and then we use that one. And that catalyst, the life, what you call carbon footprint. That will be calculated based on the input given to that one. So the program already inbuilt for each country, each geographical region where you are calculating. You can calculate for Europe, you can calculate for US also, and that is provided there. I think that is the question you are asking. Okay.
So once again, thank you, Sebastian, for the wonderful
Thank
lecture. Thank you. Thank you, the organizers, for giving me the opportunity. Thank you very much.
That was indeed an informative and enlightening session. I would like to express my sincere gratitude to Professor Sebastian C. Peter and the chair of the session, N. Manoj, for the valuable insights. Now, I would like to invite Professor N. Manoj to present the memento to Professor Sebastian C. Peter. I would also like to welcome Dr. Franklin Che, Vice Principal, Sacred Heart College, Thevara, Associate Professor, Department of Chemistry, to present the memento to Professor N. Manoj. A quick reminder, all the participants are requested to mark their attendance. Attendance sheets are provided outside the malicious hall. Participants of the oral presentation competition on the topic Applied Nanomaterials are requested to gather back at sharp 3:30 p.m. in the malicious hall. An announcement, oral presentation competitions on the topics Polymers and Biopolymers and Applied Energy Materials will commence at sharp 8:15 a.m. tomorrow at the Physics Seminar Hall in the first floor. Participants of oral presentation competition on the topic Physical and Computational Chemistry are requested to report at Malicious Hall sharp at 8:15 a.m. tomorrow. Tomorrow, we will get back at 9:30 a.m. for the Plenary Lecture 3 by Professor C. Mella Reddy. Hope you all had a fruitful session today. Now it's time for tea. Tea and snacks are arranged at the Marian Hall. Thank you.
you.